All right. We'll go ahead and get started. If anybody comes in late, they come in late. So a lot of new faces in here. That's fantastic. My name is David Spano. I own this flight school. And for those of you that don't know anything about me, I'll just let you know I've been flying for 45 years this month, 45 years ago. I've been instructing for 30 years. And this is my retirement. I stopped. I was in the building industry, and I ended that career in around 2009, 2010, and then my wife and I decided. Well, I told her when I retire, I'm going to start a flight school. So that's what I did. So that's why we're here, or that's why this company is here. All right, a lot of new faces, and one I want to introduce first is Chase Hansen. Chase Hansen is our newest flight instructor. He is in the process right now of learning how to fly these planes. These planes are different. So he's getting up to speed on those airplanes, and he'll be in the ground school at least for one rotation, just because I like all the new instructors to go through the ground school for one rotation and just kind of get a sense of how I teach it, so that in the event that I want them teaching it, they know what's going on. All right, so today is the first week of the new rotation, and it's aerodynamics, and it is obviously important to flying. How many of you, there's new faces here, so you probably didn't get the email. So what we'll typically do, if you're on the list, you'll get an email on Tuesday or Wednesday that gives you the reading assignments and what to read in preparation for the class. And it will also tell you, if you're a member of the Gold Seal Online Ground School, which we partner with them, it will also give you what areas of that ground school you should review before class, okay? And the reason I really want you to do that is because I don't really want to stand up here and lecture to people, to you guys, if you have no information. Now, I will, obviously, but if you have no information whatsoever, you have no background on what I'm going to talk about, it's very likely that a lot of it's just going to start just going right over your head. So the more background you have, the more prepared you are when you come, the more you're going to get out of this, okay? Now, I know that there's at least 4 or 5 of you that are right fresh with this and probably haven't studied anything, right? How many of you have read chapters 4 and 5 or done the ground school, the Gold Seal stuff, and have some sense of what's going on? All right. Does anyone that has studied this or has any information on this, background or base knowledge on this, do you have any questions right now about what you read? If you do, what I'm going to do is I'm going to write them on the board. I'm not going to answer them right now, but I'm going to write them on the board so that as we go through the program, when I get to that particular area, I will make sure I answer your question. So are there any questions right now that you can think of based on what you studied or read? Okay. All right. Well, I don't know if that's good or bad, but it is what it is. All right, so aerodynamics. So we can't start talking about aerodynamics without first talking about the atmosphere, all right? So without an atmosphere, we cannot fly. An airplane cannot fly. You need to have air pressure and air density and those types of things to generate the forces that are necessary for flight. So we're going to start by talking about the atmosphere a little bit, but first I want to show you a picture of something here. So there's a couple of airplanes here. This is a Boeing 737 and this is an Airbus A380. So, and you'll notice that the Airbus A380 is in the background. So it's from a perspective standpoint, it looks smaller than this one. Because this one's in the foreground. So it gives you some sense of how big this airplane is right here. So we're all familiar with this one, right? Everybody that's been on an airplane going anywhere has been on a 737, because that's pretty much everybody flies a 737. So I want to give you a sense of how big these airplanes are, because what we're talking about today is aerodynamics. And one of the questions is, how does something that big fly? This thing is huge. So I want to give you a sense of how big it is. All right, this guy right here, this 737, it's a 737-800, has a maximum gross takeoff weight of 175,000 pounds. Pretty big, 175,000 pounds. So to get a sense of the volume of it, if you took all the seats out of it and you filled it with basketballs, You could get about 7,000 basketballs in that thing. Took all the seats out and just shoved that tube full of basketballs. Okay? That's a lot of basketballs. All right? How many do you think you could get in that one?
Tens of thousands.
How many?
Tens of thousands.
Tens of thousands? Yeah. 74,000. So 10 times as much, about 74,000. This has a gross takeoff weight of 1.3 million pounds. So 1.3, think about that, 1.3 million pounds. And this thing gets up off of the ground and flies. And the way it gets up off of the ground and flies is because the air has weight. The air weighs something. If the air didn't weigh anything, if there was no weight, if there was no density to the air, this thing would never fly. Nothing would fly. Nothing would fly. Gravity would keep us stuck. Well, if there was no density there, if we were in a vacuum, we'd just be floating around, right? So the space shuttle, you guys remember, for you young guys, you remember the space shuttle? You've seen pictures of the space shuttle? So it was an airplane and it was a space vehicle. So when it was in the atmosphere, it had wings and tail structures, right? And so it had pitch, it had, you know, it could pitch, we'll talk about pitch and roll, and it could yaw, and it could do all of that while it was in the atmosphere, because the atmosphere has molecules, has air molecules, so it has weight, it has density to it. But once it got up into space, it could not do that. You could take the stick and do this and it wouldn't do anything because there was no air. There was nothing to push against the surfaces. There was no weight to anything. So now it had to have rockets. It had to have little rockets that would position the nose and do the pitch and roll and yaw. Okay, but as long as we're in the atmosphere and we have volume to the atmosphere or weight to the atmosphere, all right, then we can fly. All right, so there's the question: how can something this heavy get off the ground? So let's talk just quickly about the atmosphere. So the atmosphere, it depends on how you measure this, but if you want to get to a point where there really is just no more molecules of air, okay, you want to get out into space, you got to go about 350 miles to get out into space. Okay, so it's pretty thick. Where we fly is mainly right here in the troposphere. It's about 20,000 feet or so. And if you're in the airlines, you're up in a little bit up into the stratosphere, but unless you're flying military stuff, you're not way up into the upper levels of the stratosphere or the mesosphere. Generally, we say space begins at 60 miles. Okay, so space really we say is in here, but there's still some atmosphere up there. So when you have the reason they say space is up here is because there's just not enough atmosphere really to do much with any control surfaces. It's just so thin, there's not much you can do, okay? But there is still some weight to the atmosphere. There's weight to the atmosphere all the way out here to about 350 feet, okay? So if you were to take a tube, let's say a square inch, 1 square inch tube, and you were to set it on at sea level here, okay, and you filled it with air all the way up to the top of that 350 miles. So you got 1 square inch. I'll put it over here so it's easy to see. Let's call that's probably a little bigger than a square inch, but let's say that's a square inch. And you have it sitting on the beach at sea level, and it goes all the way up 350 miles. And you put that on a scale and you measure how heavy is the air in that little square inch all the way up to 350 miles. How heavy do you think that air would be? How heavy? What do you think it would show on the scale? The bathroom scale. What do you think? What's your name?
Jacob.
Jacob. What do you think, Jacob?
For just a bathroom scale, weigh in pounds, so probably.
How much? Nothing?
Yeah, because.
Well, it weighs something. It would weigh 14.7 pounds. That's how much it would weigh. 1 square inch weighs 14.7 pounds. That's how much pressure that it would put on that scale, okay? So as we're standing at sea level, now I'm going to preface this by saying this is a standard day on a standard day, and I'll talk about what a standard day is in just a minute, but on a standard day, and it's a benchmark that we use, on a standard day at sea level, the weight of all the air above us, all the way up to the top of the atmosphere, weighs 14.7 pounds per square inch. All right? So And that's the pressure that we feel. That's the pressure that we feel. So on every square inch of your body, every square inch of your body feels 14.7 pounds of pressure. Now, what that means for me, for the average human male, what that means is I have the weight of about 3 SUVs on my body all the time pressing against me. That's what that means. That's how much air weighs. 14.7 pounds on every square inch of my body feels like I have about 3 SUVs on my body. Okay? So the air is pretty heavy. And with that weight, with that pressure, with that force, we can now use that to our advantage to produce aerodynamic forces, namely lift, to generate a lifting action. And that's how we get a 1.3 million pound airplane off the ground, or that's how we get a 1,000 pound airplane off the ground out here that we're flying, or 2,000 pound airplane on the ground, off the ground. All right. So a couple of things I want to talk about. I want to define some things. I want to define pressure. Well, a couple things. Force. Let's talk about force. Let's talk about pressure and density. And what are these things? Because I'm going to use these words a lot today. And I want you to understand what I'm talking about when I say it, okay? And the other thing I want to talk about is a vector. Erase this for a second. A vector. I just want to define these things for you. So what is a force? A force is this. I'm applying a force to this board. It's a point. That's a force. Okay, so the 14.7 pounds, that's a force. That's a force. Okay, so force is pressure, if you will, exerted in a certain place. Pressure is weight over an area. Okay, so you could also call this pressure because it's 14.7 pounds over a 1 square inch area, right? And the force is what we feel, okay? So force is is that, if you will. Pressure is the weight exerted over an area, all right? Density is how, to put it easy, the way we're going to talk about it, how many air molecules are there in a little parcel of air. So if I have a 1 cubic foot box here, and I have 100 molecules of air in it, and I have 1 cubic box over here, and I have 1 million molecules of air in it, this one is going to be much more dense than this one. Therefore, this 1 cubic foot is going to weigh a lot more than this one. That makes sense? The more dense it is, the more molecules it has in it, the heavier it's going to be. Okay? So if you think about this column of air, this 1 square inch column of air here, coming down to the surface, where do you think the air is the most dense?
Sea level.
Sea level. Why is it the most dense at sea level?
Because there's more atmosphere.
Because there's more atmosphere above it. So it pushes down, right? And it squishes down. So you guys play football? You ever play football?
Used to.
Yeah? You ever the running back and you got the ball and they tackle you and everybody jumps on top of you? The more people on top of you, the more pressure you feel, right? Right, so the more atmosphere above us, the more pressure we feel. And the higher we get in the atmosphere, the higher you are. If you're the guy on the top of the scrum, you're up on top, you don't feel any pressure because you're at the very top, right? Just like when we go swimming in a swimming pool. You could think of a swimming pool the same way. When you're at the top, if you're up here in the swimming pool, you don't feel much pressure. But when you dive down to the drain, you feel all of the pressure of all of the weight of the air that's above you on your body. And it doesn't feel like this, right? You feel it everywhere, evenly dispersed around your body. That's pressure because it is weight dispersed over area, over your entire area. So when you're in the bottom of the pool, you don't feel like the weight is here, on your back. If you're facing down, you feel it all around you. That's the pressure. Okay, so when we're in the bottom of the ocean of the atmosphere, we feel the greatest amount of pressure. Does that make sense to everybody? Okay, we have to intuitively really grasp that and understand that, or we can never understand aerodynamics. You have to understand that, or you will not understand aerodynamics, period, okay? Because everything about aerodynamics is pressure and density. Okay, we have to have a force. We have to have pressure in order to generate the force of lift, okay? All right, so let's talk about what a vector is, because I'm going to be using vectors a lot. A vector, well, first, what's that mathematically? A line? Okay, that's a line. That's a vector. Okay? A line is what we say is scalar. It has no scale. It has no value, okay? Or it has no magnitude necessarily, or direction. A vector has both magnitude, it is that long, and it has direction, it is going in that direction. That is a vector. I'm going to use vectors a lot today when we talk about aerodynamics, because when we talk about, the way we're using vectors is we're going to be talking about force vectors. So I might be saying something like there's a force moving in that direction at that magnitude. We'll be talking about force vectors. So I could have a force vector in that direction of that magnitude. I could have a force vector in that direction, same direction, but it's not pulling or pushing as hard. Okay, or I could have one in the same direction that's pulling more, right? So that's a vector. So anytime you see a line like this with an arrow on it, in mathematics or physics, it's a vector, and it's identifying a force, okay? So I just want to get that out there because you're going to see me use them a lot and talk about them a lot. All right, any questions on force, pressure, density, and vector, and what I mean by those things? Okay. Anytime if you have a question, ask the question. If you have the question, somebody else in here has the question and it's too shy to ask it. Okay, so ask the question if you have a question. All right, let's go a little more into pressure here. And what I'm going to talk about now is the standard atmosphere. I said a while ago that I was going to discuss the standard atmosphere. Or I said that when we're sitting at sea level, when we're at sea level, the 14.7 pounds per square inch that we feel only happens in the standard atmosphere. So let's talk about what a standard atmosphere is. And this is something that's going to come up in aerodynamics. It's going to come up in weather. It's going to come up in performance. It's going to come up in systems when we talk about some of the, for instance, the altimeter on the aircraft. You need to understand these things. So what we're going to talk about right now, what I'm going to tell you to memorize right now, is something that as a pilot, this should just be there all the time, all the time. What I'm going to write on the board right now, it should just be in your head, okay? Standard atmosphere. The standard atmosphere. We have sea level. So at sea level, we're going to talk about what is the standard pressure, okay? And what is the standard temperature, okay, at sea level. Standard pressure, standard temperature at sea level on a standard day. Standard pressure could be expressed in a number of ways, but typically in the United States we express it this way: 29.92 inches of mercury. Okay, so that's what this is right here: 29.92 HG, inches of mercury. That's the standard pressure. I'll explain what does that mean. I'll explain that in just a second. It could either be 29.92 inches of mercury. You might see it as 1,013 millibars. Okay. Another way that you could talk about it, more in a force way, is that it could also be defined as 14.7 pounds per square inch. They all mean the same thing. That's pressure at sea level. Okay. So where do these two come from? Well, if you're as old as me and some of the other people in this class, we used to play with mercury in school. We used to actually, like physically in science class, you'd have a bowl and it would have mercury in it and you could do stuff with it. So if you took a bowl like this with mercury and you put a tube, and there had to be a vacuum, the tube had to have a vacuum in it, okay? And you fill that bowl with mercury, the weight, just like I said a while ago, the more atmosphere above us, the more pressure it exerts, okay? The weight of that air would push down on that mercury and it would push it up that tube 29.92 inches on a standard day. If this bowl was at sea level, that would measure, this is a barometer, it's called a barometer, okay? So it would measure the height that the air would push that mercury up that tube. If you had that bowl sitting at sea level, it would push it up 29.92 inches, or 1,013 millibars, depending on what kind of graduations you put on there. Okay, that's where that comes from. Okay, so you can just think about a bowl of mercury out there. Now, barometers nowadays aren't bowls of mercury, but okay, they're reading the same thing. When you hear barometer, what you're getting is an instrument that measures how much pressure, how heavy is the air, wherever you're reading it at. That's what a barometer is, okay? So standard pressure at sea level, the one I want you to remember is that right there, 29.92 inches of mercury, okay? The next thing that you need to remember is the temperature, and the temperature is 15 degrees Celsius. You could also, if you want, you could remember 59 degrees Fahrenheit, but I would suggest that that's the one that you really commit to memory. But it doesn't matter, but I would suggest that you start working in Celsius. Okay? Can everybody remember that? That's sea level. You have a question? I see a question.
No, I'm from Europe, so I can work with
Oh, you can work with that easy. Yes, yes. Celsius, in aviation, especially when it comes to temperature, Celsius is going to be an easier thing to work with because we use it all the time. All right? Okay, so pressure, or then you can use 1013 as well, millibars if you want, because that's something that you would work with in Europe. The only issue is that here in the United States, when you see the altimeters are all reading inches of mercury. You can get some that read millibars, but most of them are reading mercury. Okay, or inches of mercury. All right, so that's standard pressure, standard temperature. Commit that to memory. Then we have something that happens as we go up in the atmosphere. Things change. All right? As we move from sea level on a standard day and we go up, based on what we just talked about with that column of air, what's going to happen to the weight of the air as we go up? It's going to get lighter. As you go up in the pool, you don't feel as much pressure. It's going to get lighter. So the pressure is going to drop. It's going to become less. It won't be as high. So the pressure is going to decrease as we go up, and something's going to happen to the temperature. What happens to the temperature?
It's colder.
It gets colder. Why does it get colder?
Because it's getting exposed to more space because there's not enough atmosphere to keep us from the space.
You're an intelligent young man. That's not the answer, but you're an intelligent young man. Here's the answer. You ever turn the stove on at home? Put your hand down close to the heat source? It's pretty hot, isn't it? What about when you move your hand up here? It's not as hot, is it? Yeah. So the higher we get, the farther we get away from the source of heat, which is the earth, the colder the air gets. All right? So the sun does not heat the air. The sun heats the earth. And then that heat is radiated back up. So the farther we get away from the heat source, the colder it gets. All right, so we have a change of state. We have a change of pressure, and we have a change of temperature that occurs as we go up in the atmosphere. And we give it a standard, what we call a lapse rate. We have a standard lapse rate. So now we're going to talk about a lapse rate. And we refer to this in per 1,000 feet. So every 1,000 feet, we take a measurement and we say, how did it change? Every 1,000 feet. And the approximate change in pressure is 1 inch. So it decreases by 1 inch per 1,000 feet. Approximately. So if you look over here, you look at the pressure, you can see that at 1,000 feet, it's not 28.92, it's 28.86, but it's approximately an inch. Approximately an inch. It's approximately an inch up to a certain level in the atmosphere. This doesn't hold true all the way up to space. This holds true down here in the troposphere where we fly. We get up into altitudes, once you get into the stratosphere, and then things change. This doesn't hold true anymore. But where we fly, this is what we need to think about, okay? All right, so we get an approximate 1 inch per 1,000 feet, and we have a temperature change of what? Do the Celsius, it's easier.
About 2.
2 degrees. 2 degrees Celsius or 3.5 degrees Fahrenheit. That's why I like Celsius. It's easier to multiply by 2 than 3.5. Okay? All right, what I wrote here, you need to, if you're a pilot, this just better be in your brain. This is not something that you need to look up. You just better know this right here, okay? It's going to help you quite a bit as we move forward in things. All right. So that's the standard atmosphere. So the standard atmosphere has pressure and temperature at sea level, and it has a predictable rate of change as we ascend in the atmosphere, as we go up, as a predictable rate of change. All right. Now, I want to say that a lot of what we do in aviation, a lot, we refer to the standard atmosphere. How often do you think that these atmospheric conditions actually exist in the atmosphere? About big fat goose egg, just about never do they ever exist in the actual atmosphere. But that's a point, that is a benchmark. That's a place where we start so that we can do measurements on one side, one way or the other. Okay? But you have to memorize this and understand this to be able to move forward into the rest of it. All right. Now we can talk about aerodynamics. Now that we have that, let's talk about aerodynamics. Let's talk about, I want to talk about the axes of an airplane. So we have 3 axes of the airplane that we work with. We have a longitudinal axis. I don't have it, doesn't say it up here, but this is the longitudinal axis. So it runs nose to tail. Nose to tail. We call that the longitudinal axis of the aircraft. In the aircraft, and we have a movement around that, and it's roll. So this is roll. We call this roll, and there's an axis that runs nose to tail, and the airplane rolls around that axis. Okay? We have a second axis that runs in this direction. The drawing kind of shows it going through the wingtip, but it doesn't really go, or wings. It doesn't really go through the wings. It'll be down here somewhere. It'll be wherever the center of gravity is. Talk about that in a few minutes. But it goes in this direction. Goes in this direction, and the airplane pitches like that around that lateral axis. So we roll around the longitudinal axis, we pitch around the lateral axis, and then we have a third axis that runs straight up and down, and that's the vertical axis, okay? And we yaw around that axis, yaw. Any of you guys from the South? Yaw? Any yaw from the South? Okay, we yaw around that axis, okay? Next week, we're going to talk about the flight controls and the ailerons and the primary flight controls and secondary, the elevators, ailerons, and rudder, and how they control the airplane in pitch, roll, and yaw. I'm not going to get into it too much today, although I will discuss them a little bit. But generally, ailerons, roll, elevator, pitch, rudder, yaw. Okay? That's about all I want to talk about on that. So far, so good? Any of this new to anybody, or is this pretty basic, new? So, somewhat? Okay. Stop me if you have questions, all right? Don't let me get too far along, because it's going to get progressively deeper. So stop me if some foundational stuff isn't getting there. All right. 4 forces that act on an airplane in flight. We have these 4 forces acting on an airplane. We have lift and weight and thrust and drag. These are the 4 forces on the airplane. Okay. They are in, most of the time that we're flying, they are in what we call a state of equilibrium. Okay, so what does that mean, a state of equilibrium? That means that, and by the way, what does that arrow right there represent? What did I say that represents? What did I call that? A vector. Vector, vector, vector. These are force vectors, okay? Notice the equilibrium of these force vectors. That one equals that one in opposite directions. and that one equals that one in opposite directions. So there's your state of equilibrium. When the airplane is in a state of equilibrium, the total lift force equals the total weight force. The total drag force equals the total thrust force. And it has to be that way. Most of the time we're flying the airplane, a very small percentage of the time when we're flying are the forces out of equilibrium. Generally speaking, if you're moving a control surface, the forces are out of equilibrium for a very short period of time. Once you stabilize those movements of the control forces or the elevator, rudder, or ailerons, once you stop and you give the airplane a few seconds, the forces go back into a state of equilibrium. Doesn't matter whether you're climbing or turning or descending or spinning or whatever. If you are not moving the control surfaces for some period of time, the forces will go back into a state of equilibrium. Okay? All right. So it's easy to think about being in a state of equilibrium, I think, when we're in straight and level flight. So here we have, thrust equaling drag and lift equaling weight. But in a climb, it's a little harder to think about because you got a bunch of force vectors going in different directions, right? You've got lift acting here, you've got thrust along that line, you've got a drag force here, you've got weight here. There's a lot of force vectors going all over the place. And if you've done vector math, and any of you guys remember vector math? Anybody gone through vector math? Okay, if you do vector math, it's not like normal math. It's a little bit different. But all of these vectors, you can draw two vectors and then you can have a resultant vector. So for instance, right here, you've got this vector going this way, you've got that vector going that way, and that sets up a resultant vector right there, okay? So the total force of these two vectors could be said to be moving in that direction at that magnitude right there, okay? So in this example, this plane is moving in that direction, but all the vectors going that way total the vectors going that way, right? And the vectors going that way total the vectors going that way. So our forces are back in equilibrium. So what I want to get across to you is that when we're flying an airplane, this concept of equilibrium of forces is really important for you to get in your head. The forces are in equilibrium, okay? And when I delve into that formula right there in a minute, it's important that you understand that the forces need to stay in equilibrium, or when I'm talking about that formula, you have to think about the forces being in equilibrium for that to work, okay? Everybody with me so far? All right, so what does it mean for the forces to be in equilibrium? And I ask questions while we go through this. I like to evaluate while I teach, okay? So I ask questions. If I don't get answers, I pick on people. So somebody go ahead and shout it out.
When all of the forces are equal to each other?
When they're all, so we're saying that lift and weight and thrust and drag, all four of them are the same length in magnitude. They're all equal. What do you think? Let's go back here. What do you think? What's in equilibrium? Opposing forces. The opposing forces are in equilibrium. So that one's going to equal that one, and that one's going to equal that one. It doesn't mean that this one equals that one. It could, but it doesn't mean that. It doesn't mean what. When we talk about equilibrium, we're saying opposing forces. So this force is opposing that force, so these are in equilibrium. This one is opposing that one, and these go back into equilibrium. Okay? So one quick way to think about this is, let's say we have an airplane that weighs 2,000 pounds. What's the weight of the airplane? What's the force acting towards the center of the Earth? 2,000 pounds. Therefore, how much lift do I have to generate? 2,000 pounds. Okay? So that Airbus A380 that weighs 1.3 million pounds, how much lift do I have to generate? 1.3 million pounds. I get to generate 1.3 million pounds. As long as I'm generating 1.3 million pounds, guess what that Airbus A380 is doing? It's flying. Do I have to generate more than 1.3 million pounds to climb? Nope. Nope, because the forces go back into equilibrium. I don't. Nope. Forces are in equilibrium. Your total lift force is still equal 1.3 million pounds. When I'm descending in that 1.3 million pound airplane, do I need to generate more weight? Can I generate more weight? No, I can't. Now, you have other force vectors occurring, and in the climb, as an example, one force vector would be thrust, right? You've got thrust going this way, okay? But you're going this way, so you have a resultant. You have another force there that's helping with that climb. And when we talk about climb performance, when we get into the performance class, you're going to understand that climb, an airplane's climb, is a function of its thrust, not its lift. It's thrust. So we climb because we have thrust. All right. So this equilibrium of forces is important to understand. All right, let's look at the lift formula. So you see this on the wall over there. You see this on the front desk. I'm going to write it over here so that I can keep it up and I can refer to it. So lift equals the coefficient of lift times 1/2, that's called rho, and this is velocity, the square of the velocity, times s. All right, so what do these coefficients of this equation mean? So the coefficient of lift, I'll get more into this as we go through today, but the coefficient of lift means two things. There's two things that come into play here. It is the angle of attack, and I'll explain that. We're going to get to that, but just write this on your notes now. It's a combination of the angle of attack and the shape of the air. This really should say shape of the, well, it could, shape of the wing is fine. Shape of airfoil or wing. Okay. All right, and then 1/2 rho here, that's the Greek letter P is rho, 1/2 rho, and that's density. And what I say density is the how packed, how thick are the molecules of air. All right. So the density of the air, what do you think is going to happen to this value, the density of the air, when we're low to sea level versus high up in the atmosphere? That's going to change. This is going to be a higher number when we're low to the atmosphere. It's going to be more dense. As we go up in the atmosphere, this is going to thin out. The air is going to thin out. Okay? The V is the speed. How fast are we going? Now, there's a lot of speeds. Specifically, there's 4 different kinds of speeds that we'll talk about. This one happens to be true airspeed. Okay, you could write that down if you want. True airspeed, it's the square of the true airspeed. All right? And then the S, I don't know why they use S, but they use S for the wing area, surface area of the wing. So if you look at the wing in this direction like this, how many square feet or square inches or square meters or however you want to do it, what's the area of the wing? That's what this is. Okay? And notice that this formula, everything is, the lift is a product of all of these. These are all multiplied. So if any one of these, if this goes up, so this times this, times this, times this, if any one of these increases, what happens to lift? It increases. If any one of these decreases, what happens to lift? Decreases. Yeah, okay, so that's real simple. They're all multiplied together. So if any one goes up, that goes up. Right? Everybody got that? Okay. I'll come back to that here I'll leave it up here so that we can talk through it. You have in your notes what each coefficient means, right? Did you write that down in your notes? Because this slide will go away. Okay. All right, let's talk about lift. I'm going to talk about all 4 of these forces separately. We're going to start with lift. And we need to understand 3 things to understand lift. And lift is a force. Remember, it's the 4 forces. Lift is one of the forces. And it's the one force that is peculiar to aviation, right? Your vehicle that you drove here in exhibits the other 3 forces. Thrust, drag, and weight, but that doesn't exhibit lift, or you would have flown here rather than drive here. So lift is the one that's peculiar to aviation, and it's the one that's important because without it, we're not going to be flying. So we have to be able to develop a force in that direction that overcomes the weight or matches the weight of the airplane so that we can get this guy up in the air. We got to overcome that weight and get this thing up in the air, and we do that through a force called lift. And we have to understand 3 things to understand lift and how it's generated. If you read the book, the chapters in the book, two of these were talked about, and this one was not, unfortunately. But if you don't understand if you don't understand this one, you can't really understand lift. So I'll explain that one to you. But Bernoulli's principle, first of all, let's talk about that. Bernoulli was a mathematician that lived back in died in like late 1700s. But what he did is he studied fluid streams. He studied pressures in fluids, okay? And he came up with a principle that states that the speed of a moving fluid, a liquid or gas, increases the pressure within the fluid. As the speed of the moving fluid increases, the pressure within the fluid decreases. So as a fluid moves faster, its internal pressure decreases. So as its velocity increases, its pressure decreases. That's what he stated. And I just remembered as I'm talking that I forgot to say something really, really important. Aerodynamics is mathematically the same as fluid dynamics. So when we talk about aerodynamics, and you'll see liquid or gas a lot because they act the same. The same properties and the same physical laws apply to fluid dynamics, which is the study of the fluids moving and acting on bodies and surfaces. And aerodynamics is the study of air moving and acting on bodies and surfaces. They act the same until we get to the speed that air will begin to compress. Okay? So you could take a fluid. If you think about a syringe. Take a syringe. Everybody knows what a syringe is. Take a syringe and cap it off. All right, and there's nothing but air in it. Can you push the plunger down and compress the air in the syringe?
Yeah.
Yes, you sure can. Air is compressible. You can take a volume of air and make it more dense. You can compress it. That's what happens in our atmosphere. All of the weight of the air above us compresses the air down at the bottom. So it's like a giant syringe compressing the air at sea level. That's how we get more dense down here at sea level. What if you fill that syringe with water? Can you compress the water?
Yeah, whatever you do.
You can't compress the water. Water won't compress. You can't take the density of water and squeeze it and make it more dense. Doesn't happen. That's the concept of hydraulics. That's the reason we can use hydraulics to increase force on things. All right. But air is compressible. So therefore, that would mean that fluid dynamics and aerodynamics shouldn't apply. The same laws of physics should not apply. And that's true once you get to the speed where air begins to compress. But when you're in low subsonic speeds where we fly, we're not anywhere near sonic speeds, right? Not even close. So therefore, the aerodynamics that we're going to talk about in this class follow fluid dynamics. If you wanted to get a formula out of a engineering textbook on fluid dynamics, it would apply to aerodynamics as long as you stay well below the compressibility stuff. All right. So the speed of as a moving fluid, liquid or gas, speeds up, its internal pressure decreases. Okay. So what's that mean? All right. Here's my square inch. Here's what that means. Here's my square inch. If I'm at sea level on a standard day, how much force is being pushed against this wall right here at that little square inch? 14.7 pounds. 14.7 pounds is being pushed. Let's assume we're at sea level on a standard day. It's being pushed right there. Here's what Bernoulli says. When I do this, I lower it. That's what this says. This says when I do this, I'm not pushing as much pressure. That's what he's saying. So as the speed of the fluid, close to the surface there, as the speed of that fluid moves across that surface, the pressure being exerted becomes less and less and less and less and less. And the faster I blow across that surface, the less pressure is being exerted. Okay? So, I don't know how many square inches this whole wall is right here, okay? But let's say that we're at sea level and you multiply 14.7 times the square inches of this whole wall. Why isn't this wall getting pushed over? because there's another 14.7 pounds on the other side holding it up. That's why. That's why it doesn't get pushed over. Okay? But if I blew hard enough across this surface right here, I could lower the pressure of this whiteboard and suck it right off the wall. Because I'd have 14.7 pounds right behind the whiteboard pushing this way. And if I could blow fast enough here, I could lower the pressure, let's say to 5. Let's assume I could. I'd have 9 pounds per square inch pushing this way. It would suck this whiteboard right off the wall. Does that make sense? If I took this table right here, every square inch of this table has 14.7 pounds pushing down, 14.7 pounds pushing up. If I could blow air across the top of this fast enough, this table would levitate. It would be sucked up because the pressure pushing down, let's say I took it to 13 and the pressure pushing up is 14.7. Well, I'd have 1.7 pounds per square inch pushing up. I would pick this table up. Does that make sense? I'm pushing down at 13, pushing up at 15. It's going this way. Whatever's between here is going up. Okay, that's what Bernoulli said. As you speed up an air, the fluid, gas or liquid, the pressure it exerts decreases. If I'm exerting this much pressure, as I speed up the air across here, I'm not exerting as much pressure anymore. That's just the physics of it. That's what happens. Okay? So that right there in a nutshell tells you how a wing generates lift. If you get the airflow over the top of a wing moving fast enough that you decrease the pressure, the wing and the airplane that's attached to it goes up. That's the force of lift. Okay? So Bernoulli tells us, explains through this, this concept of lowering the pressure so much that the wing just lifts. And generally speaking, that's exactly what's happening. What's happening? What's happening is the pressure of the air pushing down across the top of the wing, the force of air here, versus the force of air down here. This is much lower than here. So this pressure, this higher pressure, pushes the airplane up. Or you could say it's being sucked up, whichever way you want to look at it. But the force acting this direction is less than the force acting in that direction. So we have a net force, a net vector force going that way. That make sense? Okay. What Bernoulli doesn't explain is why the shape of the wing causes the air to go faster over the top. That he doesn't explain. The continuity, the law of continuity explains that. So let's talk about the law of continuity. The law of continuity states that the velocity of a fluid flowing through a pipe equals the pipe cross-sectional area times the fluid's pressure. All right, so let me make that simple. How many of you know what a venturi is? Everybody here knows what a venturi is. You just don't know it's called a venturi. How many of you ever played with a hose and put your thumb on the end of the hose with water coming out the end and you kind of choke off half of the hose? What's the water do? Speeds up, doesn't it? That's a venturi. If you take a pipe and you squeeze down the cross-sectional area of it, fluid or water going through it, it's going to speed up. That's what the law of continuity says. Law of continuity is what gives us a venturi. So if I take a pipe, okay, and I choke that pipe off like that, all right, and let's open it up, and I blow air or fluid, air or liquid through this pipe, it'll have some velocity here, okay, and as it moves through here, the velocity will be increased because the cross-sectional area is decreased. That's a venturi, all right? So let's look at this, let's blow this up right here. All right? What's happening here is the velocity of the air here is increasing right through here. And so that what Bernoulli said is that if the speed increases, what happens to the pressure right here at the top of this little bump? It decreases. Make sense so far? So as the speed of the air increases, the pressure it's exerting decreases. The law of continuity says, okay, if I want to get the air to speed up, let me choke it off a little bit. Let me put my thumb over the end of the hose and I can get the liquid or the fluid to speed up. Okay? All right. With me so far? All right. All right, the last one is Newton's, everybody knows what this one is. Action, reaction. Yeah, you were looking for that one? Yeah.
No, I was just stuck on the second one.
Yeah, action, reaction states for every action there's an equal and opposite reaction. So I'll bring all three of these into this discussion of lift here shortly and how these all work together. But the next thing we need to think about is what is an airfoil and what are its characteristics. Can I move off this slide? Everybody have notes on this? Okay. This is an airfoil. This is a typical airfoil shape right here. So what I'm talking about with an airfoil is a two-dimensional thing. So if you were to take the wing and look at it from the side, if you were to chop it off and just look at one little section of it, that's an airfoil. This is not a wing. This is a wing. A wing is a three-dimensional object. An airfoil is a two-dimensional cross-sectional view of potentially a three-dimensional object. So when we talk about this formula right here, we're talking about this formula as it relates to a two-dimensional thing. All right? So when I show you how this works in generating lift, there are some other things at play that change total lift that result from the shape of the wing. Okay? So you see square footage here or area of wing, all right? So I could generate a lift. I could use a lift equation here and come up with an amount of lift on a particular airfoil of a particular area. But I could keep the same area, but I could change the shape of the wing and make the airplane have more or less lift as a result of the shape of the wing. Really has to do more with drag. But in essence, it would change the total lift capability of the airplane. All right, so let's talk about some things with an airfoil. Things I want you to recognize: that every airfoil is going to have a trailing edge. It's the pointy side. Every airplane is going to have a leading edge. That's the rounded side. We're going to have an upper surface and a lower surface. All right, for sure, those are easy to think about. Trailing edge, leading edge, upper surface, lower surface. Now, there's two imaginary lines that are important to understand. One of them is really important. The first one that's really important is this thing we call a chord line. The chord line is an imaginary line that moves from the leading edge, that goes from the leading edge, and it's a straight line through the trailing edge. And the leading edge of an airfoil is the tangent point. The tangent point of the curve right there. That's the leading edge. Okay? So a line, an imaginary line that goes from the leading edge to the trailing edge, that's your chord line. All right? Then we have another line that we use occasionally, or that we talk about, and we call it the camber line, the mean camber line. And that's another imaginary line that, again, it goes from the trailing edge to the leading edge, but at every point, it is equidistant. So this distance from here to here is the same as from here to here. If I drew a line here, this distance is the same as that distance. This distance is the same as that distance. That's the camber line. Okay? And the reason that camber is important is when we talk about airfoils, the more camber, when you think camber, think of curvature. The more camber the wing has, the more lift it's going to generate. The more camber the wing has, the bigger that's going to be. The bigger the coefficient of lift is going to be. So therefore, the more lift could be generated as a result of that curvature. The flatter the camber, the less coefficient of lift will be exerted on that airfoil. Okay? All right. Now let's talk about how an airfoil generates lift. And let's talk about angle of attack and all of that kind of stuff. You need to understand that. So let's take an airfoil. Here's a typical, and we have two kinds of airfoil. We have symmetrical and unsymmetrical airfoils. This is an example of an unsymmetrical airfoil, and by that I mean if you take the chord line and you look at the shape above it, there's not symmetry. Okay. Sometimes we call this a flat bottom airfoil, although they're generally not flat. There's some curvature to it, like this one shows. but it's certainly much less cambered than the top section, right? Okay. All right, so I'm generally going to be using unsymmetrical airfoils in my drawings here. So here we have an airfoil. Here's my chord line right here, you know, going through that thing right there. So angle of attack, let's talk about that real quick. Angle of attack is the angle between this chord line and what we call the relative wind. And the relative wind is the wind that is opposite or parallel to our flight path. So if this aircraft, you can picture the airplane attached to the wing here. If this aircraft were flying, let's say, in that direction right there. So this airplane's kind of doing this. Can you picture that? Okay, this airplane's doing that right there. That means that, so this is the flight path. That's the flight path. Therefore, the relative wind is opposite and parallel to the flight path. So this is the relative wind. Now you might say, well, that's the same line. Well, it is the same line. It is the same line. But there's a reason we call it relative wind. There's a reason we call the angle of attack the angle between the chord line. So that would be the angle of attack right there. We call it the angle of attack the angle between the chord line and the relative wind as opposed to the flight path, because an airplane, a wing, could have an angle of attack whether it's flying or not. So if you have an airplane just sitting on the ramp out there like this, and it's not moving, is there a flight path to it? No. But the wind could be blowing in this direction relative to the wing, and you have an angle of attack. So we call it relative wind. Okay? So I could put this airplane out there on the ramp and blow air fast enough that that plane will start flying with nobody in it. And it's not moving forward in any way, shape, or form, right? All right, so that's why we call it the angle of attack is the angle between the relative wind and the chord line, not the flight path. Just know that the relative wind is opposite and parallel to the flight path. All right, that's relative wind. Let's talk about what's happening with airflow around this airfoil as we begin moving, as we begin generating lift. Let's say this as opposed to that. Let's say as opposed to that being the relative wind. Let's say the relative wind is like this. It's coming right there. So now my angle of attack is more like that. So now I'm flying like this, right? This airflow is hitting right here. The airflow that's coming in hitting it's hitting just kind of below the leading edge in this example. But where it hits the leading edge, this free stream of air hits that leading edge, and it has to make a decision. Where it hits is actually called the stagnation point. It's called the stagnation point because the airflow stops. It stops right there. The molecules physically stop, and the streams above that stagnation point go up and over the top of the airfoil. Streams below that stagnation point go below. So you're going to have some streams of air going this way, and you have some streams of air going that way. Okay? Now, what I want you to recognize is, let's say that it's hitting right here at the front of the chord line. Look at the area. This stream of air is choking out that area of airflow right there. See that? The stream of air that's going underneath is going over a bump that's that big right there. You see that? Okay, so I want you to think about that Venturi for a minute. Let me go back to drawing the Venturi. I'm going to draw two Venturis. Okay. The velocity of the air is the same coming into the tube. Which one of these will increase the velocity more? The bottom one, right? Because I have a bigger choked off area. Here I don't have as big of a choked off area. Okay? The more area I choke off, the more I put my thumb over the end of the hose, the faster the water comes out of the hose, until I stop it off altogether, right? But the more I choke it off, the more I squeeze down that tube, the faster the air has to move. That's the law of continuity. The faster the air moves, what does Bernoulli say? The more suck, the more pressure differential, the less the pressure, the more lift force. Okay. So if I erase this, what do I have right there? An airfoil. Look at that. An airfoil. And the bigger the hump of the airfoil, the more choke, the more lift. The smaller the hump of the airfoil, the less choke, the less lift. Remember I said this camber? The bigger the camber, the more choke, the more lift. The smaller the camber, the less choke. The less I'm putting my thumb over the end, the less I'm choking the air off. Okay. So when you look at this airfoil moving through the air, you have choke on both sides. It's choking some airflow up here and it's choking some airflow down here, but it's choking more up here than it's choking down here. So what does that mean? The air going over the top is going faster because I'm choking it more than the air going under the bottom. So I'm lowering the pressure much more on top of the wing than I am on the bottom of the wing. So let's say that with the airfoil sitting still, it's not moving. Let's say that per square inch, I'm pushing down at a vector force of 14.7 pounds per square inch. And pushing up, I'm pushing up at a vector force of 14.7 pounds per square inch. That wing's not going anywhere, right? But as soon as I start moving and I get airflow going over it, now the air's going faster here and faster here, okay? But let's say that here on the top, I choke it such that the pressure is only 10. Here, I choke it such that the pressure is 11. Well, now I have a net force of 1 in that direction per square inch. You see that? That's how the wing is generating lift. That's how we're getting differential pressure under the wing versus over the wing, okay? So you have to understand Bernoulli saying as we move a fluid, as a fluid moves, I lower the pressure force. And if I'm pushing here at 14.7 pounds and I blow out here, am I lowering the pressure? No, I got to get right on the surface. And then after the break, I'll talk about this, but I got to get right on the surface. If the air separates from the surface, I'm not generating any lowered pressure. That's when we get into a stall, okay? So I got to keep that air connected to the surface. If I don't keep the air connected to the surface, I'm not lowering that pressure. This air that's blowing in the free stream up here is doing nothing to lower the pressure down here. It's this air that's right on the surface. That's what's lowering the pressure. Right down on the surface, not air that's way up here, right? So I got to keep that air connected. If that air comes separated, if that air separates, I'm not lowering the pressure. Okay. Anybody's eyes rolling in the back of their head? All right, let's take 5 minutes. Let's take a 5-minute break. Okay. I'm going to talk about stalls here, but I want to first show you. I want to show you an example of what we've been talking about. All right, so here you got a ping pong ball. So we're at sea level, right? And I got forces acting all around this ball, right? And so that ball is not going anywhere. It's sitting in that cup. Okay, but I can use the force of lift and bring this ball right up out of the cup just by blowing over the top of it. So all I'm doing, I'm using Bernoulli's principle. As I move air over the top, the pressure exerted at the surface is decreasing, and the pressure on the bottom is the same, and it's pushing the ball up. Do it. There you go. Okay, so that's lift. That's Bernoulli. That's Bernoulli. You could do it also. You could also do it if you just take a sheet of paper. You do the same thing. Take a sheet of paper. Okay, and you've got pressure exerted here and pressure exerted there. But if I blow over the top, I lower the pressure on the top. I lower the pressure. Okay, so that's all a wing is doing. That's all that's happening. As air moves faster over the top, it lowers the pressure. relative to the bottom of the wing, and then the whole thing goes up. Okay, it's a pretty simple, it's really a pretty simple thing if you understand those. Basically, we've only really talked about Bernoulli and the law of continuity. We talked about Bernoulli, which explains why the pressure decreases. The law of continuity, the Venturi effect, explains why it speeds up. The increase in velocity causes the pressure to decrease. Bernoulli just came up with this principle stating that happens, okay? The law of continuity explains why it speeds up, and then Bernoulli says when it speeds up, the pressure decreases, okay? And then I'll get to Newton here in just a minute. I haven't got to Newton yet. Let's talk about a stall. What is a stall? So we're saying that first of all, as we increase the angle of attack, we're choking off, we get more and more lift. We get more and more coefficient of lift. More and more, let me show you that real quick. This is a plot, this is a polar plot of coefficient of lift. All right, so what does this mean? So we have, along this x-axis, we have the angle of attack. So we know what angle of attack is, right? Angle of attack is the angle between what two lines?
The chord line and the relative airflow?
Relative wind. Yep, chord line and relative wind. That's the angle of attack. So as the angle of attack increases, this coefficient of lift, so these numbers here is this right here. This coefficient of lift goes up and up and up and up and up and up and up. And you can see it's almost linear. It's pretty much a straight line. So it's pretty much, as you increase the angle of attack, you're increasing lift, 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 up to a certain point. Look here, in this particular airfoil, somewhere around 16, 17 degrees or so, that lift starts to drop back off, okay? This point right here, that's called a stall. That's where the wing stalls. What's happening at the stall is this right here. Remember I said if that airflow is not connected to the surface, you're not decreasing the pressure. So what happens is, at some point as we increase the angle of attack, the air can't stay connected and it separates. Now you don't have any lifting happening here. And the wing, you have some lift, but it's not enough to counteract the weight vector, so the airplane begins to descend. So now we're in a situation where we are not in equilibrium because weight has overtaken lift and the airplane is descending not because it's in equilibrium, but because it is out of equilibrium now, okay? All right, we're not in a stabilized condition. But even if you hold that, even if you hold the stick back, sooner or later you're going to go back into a stabilized condition, but you'll be descent. The drag force this way will equal the downforce. Anyway, how do we get here? Let me draw some examples of what's happening here. Why does the coefficient of lift, the airfoil shape's not changing, so why does the coefficient of lift, why does the CL get bigger and bigger and bigger as we bring the angle of attack up and up and up? Well, what's happening is we're choking off the air. It's like, you start with your thumb here on the hose and then you close it more and more and more and more. As we bring the nose up, as we increase the angle of attack, we choke it, choke it, choke it. Here's what's happening. Let's say this is this airfoil. Let me draw it where it's a little easier to visualize. Okay, so let's say we have the same airfoil here at a higher angle of attack. Okay, I know they're not exactly the same, but try to imagine that I drew them exactly the same. All right, when we have this is my leading edge. Let's call this the relative wind. The relative wind is hitting, let's say, right here. Okay, if the relative wind is hitting right there, then this air is going this way and that way. There's my choke line right there. So I'm choking this much on top. I'm choking this much on bottom. See that? As I increase that angle of attack, the relative wind hits lower and lower and lower. And now this is my choke. I've increased the choke. Because the airflow, when the airflow hits the wing, when that relative wind hits the wing, it doesn't hit, unless you're flying like this, it doesn't hit where the cord, at the leading edge. As you do this, it begins to move down. It's hitting down here, and it actually retreats and goes back up and over the top. until you reach the stall. So that stagnation point moves lower and lower and lower and lower on that leading edge. It moves down on that leading edge, and as it moves down, now you have a bigger choke, you have a bigger bump, you have more camber. You're holding your thumb over it more. Does that make sense? The more the choke, the more you choke off the air, the faster it must go. The faster it must go, the lower that pressure gets, so the higher the coefficient of lift becomes. The more the angle of attack, the bigger that coefficient of lift becomes. Okay? So you should be able to see now that this coefficient of lift is really important in this whole lift equation. It's really important. Okay? And it is primarily the thing that we as pilots use to control lift. To control the amount of, not lift, but to control the amount of pressure differential. If I want to decrease the pressure here more, I increase the angle of attack. When I increase the angle of attack, this number gets bigger and bigger and bigger and bigger. Up to the stall. Once I reach the stall, now it goes away. So what is the stall? Okay. The stall so here we have a zero angle of attack. As the air is flowing over the top, it stays connected all the way around. You have this little tiny wake back here. The higher the angle of attack becomes, the separation begins to move further and further and further up until we reach complete separation, and the airflow can no longer stay connected in any manner, and it just burbles off the back. It just can't make the turn. So it gets to a point here where the airflow just says, oh, I can't make it around the corner anymore and stay connected, and it separates. When that happens, the wing stalls. Okay. Now here's something important that I want you to get in your head right now. The angle of attack that a wing stalls at is the same for that wing, for that airfoil shape, for that wing. If that wing stalls at 17 degrees, it stalls at 17 degrees all the time. 24 hours a day, 365 days a year. Forever and ever, amen. Always at that angle of attack. Always, always, always. Nothing will change that. If this wing, I don't know what airfoil this is or where this came from, but if this wing stalls at 17 degrees, every single time you reach 17 degrees, you're going to reach, it's going to stall. Every single time. Okay. So, what causes an airfoil or a wing, I won't say airfoil, what causes a wing to stall?
Not enough airflow going over the top of it.
Okay, what's another way of saying it? What causes an airfoil to stall? That's correct.
Not enough lift to overcome weight.
That's another way to say it. What's another way to say it? What I just said. Exceeding the critical angle of attack. We call this the critical angle of attack. Did I use that term, or did I assume that I used it? Okay, critical. If I didn't use it, it's called the critical angle of attack. So as the angle of attack increases, the point where it stalls, whatever that angle is referred to as the critical angle of attack. That's the point where this wing is going to stall. Okay? It doesn't matter what airspeed you're flying at. It doesn't matter whether the clean side of the airplane is pointed up. It could be upside down. You could be flying sideways. You could be pulling G's this way. You could be diving straight down towards the earth. It doesn't make any difference where the nose is pointed, where the dirty side, the underbelly dirty side of the airplane is pointed down or sideways or up. It makes no difference. The only thing that has to occur, this is really important, the only thing that has to occur for an airfoil to stall is what? Reaching critical angle of attack. That's it. You reach critical angle of attack, the airfoil stalls. Okay? Really important to recognize that, because we're gonna move into how weight affects things here in a minute. And you're gonna find that as you increase the weight of an airplane, the speed that it stalls at increases, but the angle that it stalls at doesn't increase. That never changes. The angle is always the same. The critical angle of attack is always the same. Okay? All right. All right, let's talk about pressure distribution real quick. I'm going to talk about this, and we'll move into some of the other forces. So so here's these vectors again. Remember, I've told you every time you're going to see vectors all over this class today. So here's a normal kind of angle of attack, if you will, shown at about +4 degrees angle of attack. And with an angle of attack like this, the pressure force, you have a negative pressure here relative to the forces around it. And then down here you have some positive force here. So this is actually giving you a little bit of, and the same with this, and not here, okay? But this would be an example of Newton's third law helping out with lift. So now you actually have some action-reaction happening because you have the angle, the wing at a point where you actually are getting some, just like when you put your hand out the window and you do this, and your hand lifts, that's Newton kind of action-reaction stuff. So you've got both Bernoulli as well as Newton, boom, Newton force happening there. You got a little bit of both going on there, okay? But one thing I want you to recognize is that as we change the angle of attack, this, what we call a center of pressure, moves. That moves. So what's the center of pressure? When an airfoil generates lift, let's take an airfoil here, and let's look at all the lift being generated. Let's just say that on the top surface, there's different amounts of lift occurring at different stations along that upper surface. So you might have lift, like this. Lift might look like this overall along the wing. So the lift distribution, might look something like that. So you could say, well, there's a center of lift. There's a point where you could take all of these vectors and centralize them. That's the center of pressure, wherever that is. That's your CP. So that's where all of these forces are acting. So at higher angles of attack, that center of pressure moves forward. As we lower the angle of attack, the center of pressure moves back. Okay? So the center of pressure on the wing changes with angle of attack, with the angle of attack. All right. Interesting story. I don't know. I'm full of useless knowledge. Back when they first started flying, when, it's kind of like the Romans that built arches. The designer of the arch had to stand under it when they took the scaffolding off. So if it caved in, it killed him and he could do no more. He couldn't do any more of that. So early aircraft designers, they were just, all right, let's try this out. And they recognized that as you're flying forward, you would have forces on the wings doing this. So they truss the wings. They put truss structures in there structurally so the wings would not fold back as air pressure, right? What they didn't recognize is the pressure distribution. As you increase the angle of attack, you'd have a force going that way. So these planes would take off and the wings would fold and break forward. They would break off. And then they recognized what was going on. They started trussing them for stresses in both directions. Anyway, a little bit of useless knowledge there. All right, this is just kind of an example, kind of showing how the airflow speeds up. Undoubtedly, you will hear somewhere some instructors say the reason that the speed of the air goes faster over the top is because it has a longer distance and the molecules have to meet at the back at the same time. That's a complete fallacy. The reason it speeds up is because of the law of continuity. So you can see here molecules, and these two molecules, as they reach here, they're brothers or whatever, but they'll never see each other again. They're forever separated in life, right? Because this is moving faster over the top. So that's all. That's just kind of a diagram of what's happening there. Okay, and you'll notice that the farther away from the choke, the less and less and less effect is occurring to the free stream air around it. All right. Spins, let's talk about what a spin is. We talked about what a stall is. A stall is simply exceeding critical angle of attack. When you exceed critical angle of attack, weight's going to take over, you're going to begin descending. You can't support the weight of the airplane. A spin is simply a stall that has a yaw, a rotating motion to it. So if picture a leaf falling out of a tree, that's a spin. That's a spin. That's what's happening. So when you're in a stalled condition, your airspeed is going to be very low, okay, and you're just descending like this. If you kick the rudder, you let some yawing occur, then you would be spinning like this, okay. So your airspeed is still low. It's just that you're rotating around like this because you have one wing, in this case, one wing a little less stalled than the other. So both of them are stalled, Both of them are in a situation where they're not generating enough lift, okay? But one is maybe generating a little bit more, one's generating a little less, and it gives you a yawing, kind of a yawing motion, all right? And recovery from that, you won't practice spins, you'll practice stalls, but you'll go over this in depth with your instructor. Recovery from that is stop the yawing, right? Stop that, so step on the opposite rudder, get it back into just a stall, and then if you're in a stall, what do you got to do to recover from a stall?
Push the nose forward so you're able to regain speed.
Push the nose forward. Decrease the angle of attack. If a stall is at or beyond critical angle of attack, if you want to be not stalled, you got to be less than critical angle of attack, so you got to lower the critical angle of attack. That's correct. Okay. All right. All right, the last thing before I move into some other stuff is I want to talk about high lift devices. I want to talk about how flaps, specifically flaps, are what we call high lift devices. So we understand we understand a little bit how a wing generates lift right now, and it's a higher angle of attack, right? We said the more the angle of attack, or the bigger the camber, right? Those things, the bigger this coefficient of lift. So if you have a plain flap, let's call this. Everybody know what flaps are? I should probably.
Generators flaps are little pieces of the wing that are able to help you make drag and more lift at lower speeds.
Yeah, you're pretty smart kid. All right, so flaps are on the trailing edge inboard, generally on the inboard right here, okay, and they will move down like this, okay? And if you look at that flap, what's happening, if it were retracted, then the wing, the airfoil looks like that, right? And so here's your camber line, here's your chord line right there. And if this is my relative wind, right, then that's my angle of attack right there. As soon as I drop that flap, this becomes my chord line, and that becomes my angle of attack. I suddenly have a greater angle of attack, and if I have a greater angle of attack, I have more drag, and I also have greater lift coefficient in that particular part of the wing, so that allows me to fly slower and still not drop out of the sky, okay? Allows me to fly slower. It also increases, this is a different airfoil shape, so now I have a different critical angle of attack for that particular airfoil shape. And usually, and what that will do is it'll allow me to get to a higher, I'll show you in a minute on another slide, it allows me to get to a higher coefficient of lift before the stall occurs. You have different types of flap, plain flap, split flap, Fowler flap, slotted flap. So split flap, you don't see a whole, you see them on 310s, you see them on some World War II, old World War II type aircraft, but a split flap is more of a drag producer, okay, than a lift producer, but it does generate some additional lift as well, because it is changing your average chord line. Fowler flap's one that you see most of the time on most airplanes, because it does two things. It increases both the camber and the wing area, because it slides out. So now when you look at this lift formula, it helps this and that. It makes both of these go up. And if both of those go up, you have an even bigger lift bump, okay? And then slotted flap, what a slotted flap does, and this is kind of what we have on our airplanes, is a slotted flap. What it does is, as this air is moving over the top and it wants to separate back here, the air moving under the bottom kind of goes, it gets energized through there, and that energetic air, that high energy air, kind of sucks and pulls the air back down, keeps it connected farther back.
It's kind of like blown flaps on like the big 21s, where it takes some air from the compressor and blows it onto a little flap. It's sort of like that, out the air being pushed from the compressor.
Here, let me give you this microphone.
Sit out there.
Yeah, just, you get over here and teach this. You're correct. That's exactly what it's doing. It's exactly what it's doing. It's energizing that airflow. Okay. All right. When you get into airliners and stuff like that, here's an example of what you would have. So here again, this is the plot of the coefficient of lift that I showed you, right? So in this example, this is more of an airliners type airfoil, because it has flaps, Fowler flaps, and they have multiple, not just one, but two, and they also have leading edge slats that can come out the front. So the wing gets much bigger and much more camber, right? So when the wing is in a cruise clean configuration, you can see that here's my coefficient of lift line. So that's this right here. It's my coefficient of lift line. But if I put takeoff position flaps, I get a lot more coefficient of lift before stall. A little lower angle of attack before the stall, but a lot more lift. Now I put all my flaps in for landing. Now look at my coefficient. Now look what that airfoil does to me. So I've essentially got, in this case, what's shown is 3 different airfoils for that same wing. So that allows these bigger, heavier airplanes, and this is how an airplane like that A380 that weighs 1.3 million pounds is able to take off. All right, if we want to generate enough lift for that airplane to take off, we got to generate some lift. We can't do anything about the density of the air we're in, right? We're either flying at sea level or we're flying at 10,000 feet or whatever the density of the air is. We can't do anything about it. Okay, we can't. We change the speed as we start moving, but really what we have control over is this and this, okay? Well, I control this here, all right? But I can now also control this to a big extent with these slats and flaps. And so that's how I can generate so much lift on this big behemoth airplane and get off the ground at a slower airspeed so I don't need 5-mile long runways. And I don't have to be going 300 knots before I have enough speed to take off, okay? Okay, let's move into, before I move into it, lift in general. Questions? Questions on lift? Okay, let's move into drag. So drag doesn't oppose lift, but it's the other one that takes a little while to explain. Not quite as much as lift does, but it takes a little bit to explain. All right, so drag is the force that retards thrust. And we have 3 kinds of, we have 2 general types of drag. We have one that we're all familiar with. That's what we have up on the slide right now. And that's called parasite drag. And parasite drag, everyone in this room is familiar with because we've lived on the planet for some number of years. And we know that the faster we move through this liquid we call air, the more drag we feel. If you sit at a stoplight and you put your hand out the window, you don't feel anything if there's no wind. As soon as you start moving, you feel it. And the faster you go, the more of it you feel. That's drag, that's parasite drag. We have 3 kinds of parasite drag. We have form drag, interference drag, and skin friction drag. And form drag just speaks to the shape, okay? It's the shape. So here, if I'm looking at the side, I have a, let's say a silver dollar. Let's call that a silver dollar. You're looking at it from the side. Well, if I'm trying to move that silver dollar through the air like this, the air is trying to get around that sharp edge, and it generates this wake of turbulence behind it. Well, that's the drag. That's parasite drag. That turbulent air coming off the back is parasite drag. Well, if I enclose that silver dollar in a sphere, let's say, and I move that through the air, well, now it's a little more aerodynamic shape, and the airflow can get around it, and I don't have as big of a wake area behind it, so I've lessened the drag. If I then elongate that out a little bit more, I give it even more area to come back together, and I have less and less parasite drag. And there's a point where I get this to an optimum shape where it's as little drag as possible coming out the back, okay? So if I were to look at this from the front, if I were to look at all these at the front, it looks like this. Okay, that's what it looks like. That's what the airflow sees, but it goes around that in different ways depending on the body I put around it, the aerodynamic shape I put around it, okay? So from a drag standpoint with airplanes, generally when you look at the fuselage of an airplane, we're trying to design something that looks like that. We're trying to get something that has a shape that the air can flow around and come off the back and not leave this giant turbulent wake of airflow behind it, okay? So this this shape of the fuselage, we want to make it as aerodynamically clean from a form standpoint as we can. All right. Problem is, what do we need? We need to generate lift. So what do we use to generate lift? We use wings. So we got to attach a wing to it, to this nice aerodynamic shape. We attach a wing, and everywhere we attach something to this beautiful aerodynamic shape, the airflow now, that thing interferes with the flow of air around it, so now we have interference drag. Everywhere something touches my nice shape, struts, landing gear, wings, antennas, anything sticking out is going to generate interference drag. Okay? So we have form drag, we have interference drag, and we have what's called a skin friction drag. And the skin friction drag is just taking the entire surface area of the body of the airplane, and you have frictional forces. As the air is trying to go around it, there's frictional forces. So the more skin there is, the more force, the more drag is going to be associated with that. Okay? So those are your parasite drags. These are pretty easy to recognize. They make sense to us. The one that's not as easy to recognize is the one that's called induced drag. Induced drag is a byproduct of lift, or it is induced by lift. So your car that you drove here today in has all of these. Your car has all of these drags associated with it, every one of them. Your car doesn't have this, okay, because your car doesn't generate lift, all right? So induced drag is induced by the product of lift. And I believe I have a, yeah, let me just move to this slide just real quick and I'll come back to the other one. All right, so this is a total drag plot, all right, and it has both types of drag on it. It has parasite drag on it, and it has induced drag on it. I want you to notice that here's speed along the x-axis, and here's drag along the y-axis. And let's focus on parasite drag for a minute. So think about your car. The faster you go, what happens to the magnitude of drag? It increases, so we can see that right here. The faster we go, the more drag we feel, the more drag the body, the car, the airplane, whatever, has on it, the larger that force. The induced drag, notice, is backwards. The slower we go, the higher it is. And the faster we go, the less it becomes. All right, so they're inverse to each other, okay? So why is that happening? Well, a couple of things are happening. Let's go back to the airfoil here. And first off, let me draw an airfoil at a lower angle of attack. Let me draw one at a higher angle of attack, assuming that this is our relative wind right there. So you can visualize the, zero angle of attack and some high angle of attack. Everybody can visualize that? Okay. So the lift that's being generated on the wing is being generated perpendicular to the relative wind, okay? So if this is my relative wind, I have a lift force acting in that direction, okay? Lift force acting in that direction. Perpendicular, okay? But I also have a lift force that now is tilted somewhat as a result of the effective downwash. So as this airflow comes over the top of this wing, it doesn't get over here and then just do that. There's going to be some downwash effect right here, just from the air flowing off the top surface, as well as some vorticity, which I'm going to talk about in a second. But there's some downwash, and there's going to be maybe even a little bit more here, because I have a higher angle there. This downwash has an effect of tilting an additional vector backwards, like this. Okay? When you have two vectors, you have to connect them. So that means I got a connecting vector that goes that way, and a connecting vector that goes that way. That is induced drag, right there. That's induced drag. Which one of these drags is higher? The one on the bottom. Now let's think about speed. Which one of these airplanes is flying faster? The one on the top. The lower the angle of attack, the faster we fly. So when we're flying, and I think, I didn't really talk about this, I took it for granted that everyone understood it, but if I'm flying like this is flying slower than that. This is faster flight. The lower the angle of attack, the faster we're going. The higher the angle of attack, the slower we're going. Okay? All right. So the slower we go on the speed scale, the slower we go, the more drag, the more induced drag is being generated. All right? That's one way of visualizing induced drag. Another way of visualizing induced drag is here. That's a visual representation of induced drag right there. Okay? We also refer to this as wingtip vortices. So what's happening here is picture lift. We all understand how lift is generated. If you had to quickly and just succinctly define why does a wing generate lift, how would you do it? Just quickly, how would you do it? Using pressure. Differential pressure. Low pressure on top, high pressure on bottom. That's how a wing generates lift. By moving through the air, you set up a low pressure area on top of the wing relative to a higher pressure area on the bottom of the wing, and we generate a net force up, okay? So now think about that. As this air is coming up here, it's got a wing to push on, but then all of a sudden there's no wing. Where's that air go? Comes right off the back. So as we're moving forward, this air, boom, comes right off the back, and we have this giant spiral of air spiraling off of the wing. Okay, that's a vortex or a wingtip vortex. All right, that happens all along the trailing edge of the wing, but it's most pronounced back here. You have some vortices, you have some downwash and tilting of the air coming off the back surface of the wing, which is generating induced drag, and it's most pronounced right here at this wingtip where you get these wingtip vortices. Okay. You can picture that as a disruptive flow of air that's backwards, a retarding force. Well, you're not going to get that retarding force off of that wingtip unless you're generating a pressure differential, right? So when we generate the pressure differential, we generate this wingtip vortice, and that is induced drag. That's what induced drag is. The bigger the pressure differential, the bigger this is going to be. So if I'm flying like this at a low angle of attack, the difference in pressure on top and bottom is smaller. So it's a smaller little wake. The higher the angle of attack, in other words, the bigger the pressure, the higher the angle of attack, the more I'm choking off the air. The more I choke off the air, the bigger the difference in pressure. The bigger the difference in pressure, the more it's trying to go up, boom, the bigger the vortex that's going to come off the back side of it. Does that make sense? So I'm going to get much more induced drag. I'm going to get much more wake turbulence, much more vortex flow off of the tips of the wings, the higher the angle of attack I am, because another way of saying it is the bigger this number right here, the bigger that coefficient of lift, the more wake turbulence I'm going to have, the more induced drag I'm going to have. The more I'm flying like this, the bigger this guy is going to be, the bigger this is going to be. Okay? That's induced drag. All right, let's talk about ground effect, because ground effect is a thing that occurs when we're close to the ground, and what it is it's a reduction of what we just talked about. It's a reduction of that induced drag. So as we get closer to the ground, these vortices that are coming off of the wing hit the ground. So if you looked at it from the front like this, if you looked at it from the back, these vortex up in the air, they extend back, and the longer that vortice is, the more drag is being generated. But as you get close to the ground, boom, it gets stopped. The ground affects it. The ground affects the vortex. It affects the induced drag. It essentially lowers or eliminates. It lowers or eliminates. Where's it at? It lowers or eliminates this line right here. Okay? So total drag, if I were to plot my induced drag and my parasite drag together, if I plot them together and got rid of the lines individually, I would have this total drag line right here. That's the total drag on the airplane, both parasite and induced. If I were to get rid of that part, this would look different. You'd still have some induced, but it would look different. Essentially what you'd end up with is a total drag curve that looked more like that. It would just be a different shape. You're reducing the amount of drag, you're reducing the amount of total drag on the airplane because you've gotten rid of one of the two components of drag. Okay? So how many of you are flight training already? Okay. Have you noticed when you come into land, the plane tends to float? You come in and you round out on the runway, and then it just like, man, it doesn't want to land. It wants to keep on going. Well, the reason is we have lost this component of drag, and we are able to fly more because we've lost that component of drag, because the ground, we've gotten close enough to the ground where it has begun to affect the characteristics of the airplane. The ground had an effect on the characteristics of the flying characteristics. So we call it ground effect. When you get close to the ground, it affects the flying characteristics. And the way it affects it is it reduces or eliminates, the closer we get, what? It reduces or eliminates what?
Drag.
What kind of drag?
Induced.
Induced drag. It eliminates or reduces the effect of the drag that is produced by lift or is induced by lift. Okay? So drag is important to understand, and when we increase lift, we increase drag. You can't get one without the other. So when I talked about the camber airfoil, airfoils with higher camber generate more lift. Well, when they generate more lift, they also generate more drag. The more lift an airfoil generates, the more drag an airfoil generates. So there's a sweet spot. Well, there's a trade-off that has to happen when we're flying airplane, when we're designing airplanes, specifically airfoils. We design an airfoil to do certain things to meet the requirements of the airplane that's being designed, and there's a lot that goes into the shape and the choice of the airfoil that's used, because you want to maximize lift and you want to minimize drag, right? Too much lift is too much drag, and so you got to find that sweet spot. I want it to fly really fast, but if you want it to fly really fast, you're going to have a thin airfoil. Okay? If you have a thin airfoil, you generate less drag, but you also generate less lift. And if I'm generating less lift, I got to be going faster to make that work. You see? So there's trade-offs that have to happen. Okay, any questions on drag? Okay, let's talk about weight. This force is the easiest one to understand, I think. But when I talk about weight, I want to talk about two kinds of weight. I want to talk about the one that we're all thinking about right now, and that is how much do you weigh? If you step on a scale, what do you weigh? If you put an object on a scale, what does it weigh? So I'm going to call that scale weight. So if the airplane weighs 2,000 pounds, what's the weight of the airplane? 2,000 pounds, and that would be what I'm going to refer to as the scale weight of the airplane. Okay? We have another kind of weight, something I refer to as an aerodynamic weight. Okay? So if I were to take, as an example, let's say I took a half a pound object on a string, hanging on a string right here, and I had it hanging down. And I could perfectly calibrate my arm, and I knew that weighs a half a pound. Its weight would be a half a pound. But if I started swinging it around in a circle, would my arm still feel a half a pound?
No.
It would feel less or more?
More.
More. Okay, well now that's an added weight. That's an added load factor to the weight. So I've added something that I call load factor. All right? So let's take this airplane right here, and let's say that it weighs 2,000 pounds. Therefore, how much lift must I generate? 2,000 pounds. Well, one would think that would be correct, but it actually needs to generate a little bit more lift than that. Okay? Because we have to, and that weight and this factor, what we call this lift right here, that's being carried by the wing, is what I want you to think about from now on as load factor. So the wing is carrying the load of the airplane. And how much load is it carrying? Is it carrying just the weight of the airplane, or is it the weight of the airplane plus some additional factor? Okay? That's load factor. So you could probably, I think, visualize if you're in the airplane and you're flying like this, there would be some force going that way. Right? So if the airplane weighs 2,000 pounds in this direction, or in this direction, right? And let's say you're just flying straight and level like this, then the load factor on the wing probably is 2,000 pounds, or maybe it's actually a little more. I'll explain why in just a minute. But right now, for what we're talking about, let's say it's 2,000 pounds. All right? What if I were to pull back really hard and we did this real quick? Would the airplane's wing be carrying more load than 2,000 pounds during that maneuver? Yes, we've added load to the wing. We've increased the load factor on the wing simply by maneuvering the airplane. This is something you can't really do in your car. Well, actually you can. If you go around a corner real hard, you have an additional force going that way, right? You can do it in your car too. You can increase the sideways load. All right? So that's load factor. So when we talk about weight and we talk about what the wing has to hold, it's not just the weight of the airplane, it's the entire load on the airplane. So that includes the weight of the airplane plus whatever aerodynamically we're doing to it. Okay? So let's picture this airplane like this. Here's my airplane. It's flying at you or away from you, whichever way you want to look at it. And if we have, and for just a minute, I'm going to say that we weigh 2,000 pounds. So there's my force vector in that direction. My lift force vector has to equal it at 2,000 pounds in order to be in equilibrium, right? We have to be in equilibrium when we're flying. Okay. Now, what if I turn the airplane? I bank the airplane. Here we're in a turn. Okay. Weight this always acts straight down towards the center of the globe, towards the center of the earth. So that means that weight is acting straight down, just like that. So I've got this component acting straight down even though I'm turning, even though I'm doing this, weight still always acts directly straight down towards, or gravity, okay? I still have to have the component opposing that going straight up at 2,000 pounds. So I've still got that component right there, right? But now I'm going to, if I want to hold altitude, if I just do that, I'll just descend. I'll turn, but I'll descend, okay? But if I want to maintain altitude in that turn, I've got to pull back. I've got to increase that angle of attack a little bit. And when I do that, now I set up a resultant force in this direction, perpendicular to the wing. And if I want to maintain altitude, I have to get that resultant force all the way to there. It's got to go all the way to there. If it doesn't go quite that far, if I only pull to there, I'll still turn, but I'm going to descend through that turn. That make sense? I've got to pull it so that the vector, this force vector, gets up to my 2,000 pound force vector. All right? And in doing so, I've set up another vector right there. This vector is called the horizontal component of lift. Horizontal component of lift. That's what makes an airplane turn. So if you get a test question on what makes an airplane turn, what's the answer? The horizontal component of lift. That's the answer. So when you do this, when we're flying like this, we have one vector pointing that direction. As soon as we bank it, we set up two more vectors. We get a vector going here, and we get a connecting vector going there. This one going this way is the horizontal component of lift. That's what causes the airplane to turn. If we want to maintain altitude through that turn, we have to pull back and get another force vector up here that gets all the way up to here. That's a resultant lift vector, all right? When we do that, now we set up another opposite and equal vector in this direction. Okay? Let's say that 2,000 pounds of force takes us to here. Okay? Well, this additional force right here, this additional load, has to be added to the 2,000. So let's say that's 1,000 pounds worth of force plus the 2,000 pounds worth of force. Well, in this condition, I can't generate 2,000 pounds. I need to generate 3,000 pounds of load on that wing to maintain altitude through the turn. I have increased the load factor on the wing. So when I'm straight and level, I have 2,000 pounds of load on the wing. In the example I drew, when I bank, if I just bank, here's my airplane. If I just bank the airplane, if all we do is bank the airplane and I don't pull back, I still set up a horizontal component of lift and I will turn, but I will descend through that turn. So I'm not really increasing the load on the wing. I'm just descending through the turn. But if I bank and I do this, Now I've got a resultant force, which is the G force that we feel. I've increased the amount of weight, the amount of load that the wing is carrying, and the load factor increased on the wing. It had to increase in order to maintain altitude through that turn. I get a feeling not everybody's following me. Everybody, well, I know you. I'm pretty sure you are. Anybody lost so far on what I'm talking about? Everybody understand this? We're talking about the weight, the load that the wing is carrying. So in this turn, in this level turn, I have to increase the G-force. I have to increase the load, the amount of weight that the wing is carrying. Okay? So that's load factor. So when we talk about weight, I have just the weight of the airplane if I put it on the scale, and then as I maneuver the airplane, I also increase the load that the wing is carrying simply through the act of maneuvering the airplane. When you get in your car, if it weighs 1,500 pounds and you go drive around, the weight lessens because you have some nominal fuel burn going on, right? But you don't have giant changes in the load that the wheels are carrying. You get in an airplane, you're changing the weight constantly. The weight the wing is carrying is constantly changing as you turn, as you maneuver the plane. The load that the wing is carrying is changing because of the forces that are acting on the airplane. Okay, that's weight. Everybody with me on that? All right, we'll tie some of this together as we finish out here. All right, let's talk quickly about thrust, and then I'm going to come back and talk about stability and things like that. Thrust is the force that overcomes the drag. So that's the thing that gets us moving forward. Generally in the planes we're flying, we use gasoline-powered combustion engines that are turning a propeller to provide the thrust. But thrust could be generated through rockets or jets or piston engines like we have, or electric engines for that matter. Turboprops. Could be a lot of ways to generate thrust, okay? You don't even need an engine to generate thrust. If you look at a sailplane, at a glider, it doesn't even have an engine. It needs a tow plane typically to get up in the air, but once it's up there, it uses energy management in a different way. But anyway, thrust is the forward force that's counteracting drag. Okay, so how do we generate the thrust? As I said, we typically use what we're using is a piston engine, so that's what I'm going to talk about. Piston engine driving a propeller. I'm not going to spend a whole lot of time on it, but I'll give you some general idea of what's happening. If we look at in this condition, let's say we're looking at the side of the airplane and the side of the propeller sticking out of us. Okay, pretend it's not moving. The engine is running, the propeller is turning, but we're not moving forward at all. In that case, forget this line right here. In that case, here's my chord line right here. And by the way, what's that propeller? That's an airfoil. It's just an airfoil. Just like a wing, okay? So that's my chord line right there. And in this case, my angle of attack or my relative wind would be right here. So that would be my angle of attack right there if I weren't moving, okay? I would have, in this case, no forward velocity. But as soon as I start moving forward, okay, as soon as I start moving forward, if I'm moving this fast, that becomes my angle of attack. Or that becomes my relative wind. If I'm moving this fast, that's my relative wind. If I'm moving this fast, that's my relative wind. So you can see that the faster I go, the smaller my angle of attack becomes. Do you see that? So as we move forward, as we fly faster, the angle of attack decreases and decreases and decreases and decreases. So you're going to reach a point on a propeller-driven airplane where you're not going to go any faster. You can't go any faster in level flight because you can only develop a certain amount of thrust or a certain amount of lift. So lift on a propeller, we term it as thrust, but it's lift in that direction. All right, so on a propeller-driven airplane, especially a fixed-pitch propeller, there is a point where the engine and propeller combination, that's as fast as you're going. Engine and drag characteristic of the airplane. That's as fast as you're going, okay? So that's how a propeller is operating. It's just an airfoil operating in that direction as opposed to, this way. All right, effective pitch and geometric pitch, just real quickly. Geometric pitch would be if you took a propeller, okay? And you know how a propeller's twisted, kind of like this? I'll explain what this all means here in a minute. How it twists as it goes out. If you took that propeller and you put it in a medium like Jello, let's say, that's pretty dense, and you took it and you turned it 360 degrees, the distance that it would move forward is the geometric pitch. So if you have a propeller that has a 62-inch pitch, that means that in Jello, if you turned it 360 degrees, it would move 5 feet. It would move 62 inches forward. That's the pitch of the propeller. The effective pitch is how far it actually moves in the air, and then the slip is the difference between the two. So we're not flying in Jello, right? So we're flying in air, and the denser the air, the more effective pitch you would get. So the lower the atmosphere, the closer to the 62 inches you would actually move. The higher in the atmosphere, the thinner the air, the bigger the slip, the less you would move. Does that make sense? That's just the way we talk about propellers. They have an effect. We talk about, propellers have 4 numbers. They have a pitch and a diameter. So you have, you might have a 60, 62 or something like that. So 5-foot diameter, it would move 62 inches in Jello. Okay, you don't really need that information for too much, but there it is if you ever want to know it. All right, why do we have this? Why does the propeller do this? What is that? First of all, these are airfoils. And those airfoils are all set at different angles of attack. So now let's come over here and look at this formula. First of all, when we're flying through the air, let's look at a propeller from the side. Let's do this. Let's say that here's our propeller. We're looking down at the airplane, okay? And what we want as we're flying is we want the amount of thrust or lift that's being generated right here. We'd like it to be the same as what's generated there, or there, or there. So we'd like an even, if we could, an even thrust distribution, wouldn't we? All right, so we want an equal L. We want the L in that formula. We want the L, or the lift, to be the same along the span of the propeller. Well, the only way we can do that is by varying some things here. That's why we have twist and we have different shapes. So let's come back to this formula. We can't do anything about the mass of air or the density of the air that propeller's turning in, right? It is what it is. We're at whatever altitude we're at. Can't do anything about that, okay? The speed of that propeller is changing along the chord. So here, if I have whatever my rotational velocity is, this part of the propeller right here is spinning much slower than the tip is, right? It's farther away. So this is moving a lot faster than this is in here. So this speed is varying. This thing is varying all over the place along the span of this propeller. So if I want this to be equal, I say I want it to be 50 or whatever. I want it to be 50, okay? I got to change this, and I got to change this along the entire span so that it equals 50 all the way across. And the way I do that is by changing the coefficient of lift, which is the shape of the airfoil and the angle of attack, and the size of the wing. So the size changes at each station, and its angle of attack changes at each station, so that I get back to something that resembles the same force along the entire span of that propeller. Make sense? That's why they twist. That's why they do what they do. That's why it's fat and thick at the hub, and thin and small at and a low angle of attack at the tip. Does that make sense? Why we would do that? Okay. Propellers, by the way, are very inefficient. We develop, generally speaking, if you have a really well-designed propeller, you might get 80%, 75 to 80% of the shaft horsepower that's going to that propeller ends up turning into actual thrust. So to put that in perspective, our airplanes, our 100 horsepower engines, the shaft, the power that's actually getting to the propeller isn't 100. We're losing some. We'll talk more when we get into systems about that. But let's say we are able to get actually 100 horsepower to the shaft that the propeller is attached to. If we can get 100 horsepower there, about the best we can do as far as thrust is 75 to 80 horsepower, because we lose so much efficiency out of the propellers. You just can't get 100% effective propeller. All right, let's take another quick 5-minute break, and then I think I might actually be able to get through this whole thing. Okay, we'll go ahead and get started. I want to kind of, we've talked about all the different four forces, but I want to kind of I want to talk about some things that kind of tie some things together a little bit. I talked about load factor, and I talked about stalling. All right, what did I say about stalling? What is it you got to remember about a wing stalling? What's the most important thing to remember?
The
Critical angle of attack. So an airplane wing, the wing will stall when you reach the critical angle of attack. That's the most important thing to think about. All right. There can be confusion when you start training when it comes to stalling the airplane, because one of the things you're going to do in training is you're going to practice stalling the airplane. All right. And we're going to relate specifically two different kinds of stalls with two specific airspeeds that will result when the airplane stalls. Okay. So, and we call them VSO and VS1. So those are two stall speeds: velocity stall in the landing configuration and velocity stall in the clean configuration, or the cruise configuration, if you will. So, and we relate those to two specific airspeeds that you'll see on the airspeed indicator. All right. The thing that I want you to understand is that will occur if there is no additional load on the wing. Okay. So, but the reason that we say an aircraft can stall at any airspeed and at any attitude is because if you're applying any load on the wing, you will stall at a faster airspeed than what we do when we practice. So I just want to be clear on that. So I want to show you two things. This is in the book. It's figure 539 in your book, but this chart has stall speed and load factor on it, and I want to show you something. Bank angle and the percentage of increase in stall speed. Okay, so if your wings are level, you have and typically when we practice those two stalls I told you, VSO and VS1 stalls, we're usually doing it with the wings level, which means we're doing it right here. So the angle of bank is 0. So if the angle of bank is 0, is there any increase in stall speed? No. There's no increase in stall speed. So let's say that on our airplanes, let's just use we'll use them both. So VSO equals 45 indicated, and VS1 equals, it's 51, but we'll call it 50 indicated. So that means in our airplanes, if we're in the landing configuration, in other words, the flaps are down because we have fixed gear, so we can't bring the flaps up. So the flaps are down, full flaps. We will stall when the airspeed shows 45. If we have the flaps up in the clean configuration, when you hear me say clean or dirty, what I'm talking about is drag. Talking about drag. Is the airplane draggy or not? Are we clean from a drag standpoint, or are we dirty? When we have flaps down and gear out, stuff like that, we're dirty from a drag standpoint. So this is a dirty stall, and this is a clean stall. We also refer to this as an approach to landing stall. So the flaps are down, the gear is out, we're ready to land. This is a departure stall. The flaps are up, the gear is up. We're not attempting to land. We are clean from a drag standpoint. It's a departure. We're taking off. We're clean. A landing. We're dirty. Flaps are down. Flaps are out. Gear is out. All that kind of stuff. Okay. Just so you understand that. So when we're at 0 bank, if the flaps are up, we'll stall at 50. But if we're banking 60 degrees, look what happens. Come straight up here, there, and there. What's our load factor? Oh, this way. What's our load factor? 2. So when you're in a 60-degree bank turn, if the airplane weighs 2,000 pounds, how much load is the wing carrying? 4,000 pounds. You've doubled the load factor. Okay, and what's the stall speed increase approximately? 40%. So that means we're not going to stall at 50, we're going to stall at 70 in a 60-degree bank turn. stall speed, and you'll notice that as you increase the bank, what happens to stall speed? It increases. What happens to load factor? It increases. So if we're not dead level with the wings, if our wings are like this, both our stall speed and our load factor have increased. So understand that. All right. When the stall occurs, if the stall occurs right here, let's say in this example, just prior to the stall, the wing is carrying 2,000 pounds and the speed is 70. But at the stall, what's the angle of attack? Critical, whatever it is. So no matter where you stall it, the angle of attack doesn't change, but the load and the speed change throughout the entire thing. So that's why I want you to really understand that what needs to happen for a wing to stall is not a speed, it's not a load factor, it's an angle of attack. When you reach that angle of attack, it's going to stall. And it will happen at something other than this if you're at some bank. And when we practice stalls, we practice zero bank. Usually, we'll do some turning stalls as well. We'll do some turning stalls. But generally, when we talk about VSO and VS1, what we're saying is these are the stall speeds when we're at a 0 degree bank. In other words, we have not increased the load factor. Okay, understand that. All right, everyone understand that? Okay, all right. All right, let's see. I want to talk about some weight effects and balance effects, and then I'm going to get into a little bit of stability. Let me blank the screen for a second here. Okay, so let's take an aircraft here. Let's take an airplane. I'll get out of the way for people behind me here in just a second. Okay, so there's an airplane flying in that direction. And I said we talked about the 3 axes of the airplane, right? What were the 3 axes? Who remembers that from way back in the beginning? Well, the axes, that's the movement.
Longitudinal, latitude.
Horizontal, vertical,
Lateral, longitudinal, vertical. Lateral, longitudinal, vertical. Vertical, lateral, longitudinal. And there's the lateral going that way. And they all come together at this point right here that we refer to as the center of gravity. That's the center of mass of this particular object, which is an airplane in this case. Everything has a center of mass. This bottle has a center of mass. This bottle has a point where all of the weight is concentrated in one place, has a center of mass. So the airplane has the same thing. We've got a center of gravity. So this is where weight acts. Weight acts straight down through that center of gravity. Okay? When we're flying, remember I talked about the center of pressure and the center. I didn't really talk about the center of lift, but it is kind of that center of pressure. That's the center where the lift forces are being generated. Generally speaking, those lift forces are designed, or the airplane is designed such that the lift force acts behind the weight force. So they don't act directly opposite. They're not coplanar. They're equal in force. They're equal in magnitude, but they don't have to act in the same place. So I can have a force vector acting here. This force vector acting there is the same magnitude in the same direction, but laterally they're offset a little bit. Make sense? And that's kind of what's happening here. I've got weight over here, and I've got lift over here. I've got lift acting back here, and I've got weight acting back there, or up in front of it a little bit, right? So what is that going to do? We're going to set up another force, right? If I have an axis, if I have a board across here, and I pull up on the board here and pull down on the board there, where's that board going? Going that way, right? So that sets up a moment, a turning, a moment force. So we have a nose down moment. We have a nose down moment because of where the center, where the weight acts versus where the lift acts. We also have it because the airflow around an airfoil itself causes because of the pressure distribution, causes the airfoil to want to tumble in that direction. So we have moment forces causing the nose to want to go down. All right, well, what do we do about that? Well, when we're flying, well, we don't want to fly through the air like this. That wouldn't be comfortable. We'd all start throwing up pretty quickly, right? So we have to stop that from happening. How do we stop that from happening? How do we stabilize that from happening?
We move the lift and the weight closer to this.
Okay, well, you could do that.
Back pressure,
You're smart. You could do that. What does the back pressure do?
like just increasing the elevator. So
We have a something back here that we call a horizontal stabilizer. So we have this surface back here, which is called a horizontal stabilizer. That horizontal stabilizer has to counteract this nose down pitching moment. So we have a force in that direction, a stabilizing force back here that keeps us from tumbling as we go through the air. Okay? Well, let's say let's go back to what I've been talking about. I'm generating 2,000 pounds here. I'm generating, and now we're not applying any additional load by maneuvering the airplane. We're just flying straight. Okay? All right, I weigh 200 pounds. I feel like I weigh 200 pounds in the seat. I'm not applying any load factor, G forces to my body or to the wing. So what does the wing have to lift? 2,000 pounds, right? Wrong. It's got to lift more than 2,000 pounds because it's got to lift this weight plus this weight. All right, so let's say I need 200 pounds of downforce back here to keep the nose from tumbling. Well, my load factor is not 2,000, it's 2,200. So just understand that even in straight and level flight, unless you have a situation set up like this smart guy said right here, a very intelligent guy, where the lift and the weight are exactly opposite each other, you're going to have a tail down force back here. And so you're going to increase the load on the wing a little bit. All right. So we're getting into talking about how do we keep the airplane stable and what is a stable airplane. All right. So when we talk about stability of an airplane, I'll get into this a little bit here. All right. When we're talking about stability, we're talking about stability around all three of the axes. So we're talking about stability longitudinally. We're talking about stability laterally. And we're talking about stability around the vertical axis or on the yaw. So we're talking about pitch stability, roll stability, and yaw stability. So everything I'm going to talk about right now, I'm going to talk mainly about it in pitch because it's easier to visualize that way. I'm going to talk about it in pitch, but what I'm talking about applies to all three of these axes of movement, okay? All right, so when we talk stability, we have two kinds of stability. We have static stability, and we have dynamic stability. Two kinds of stability. And by definition, these kind of sort of meet the definition of static and dynamic. But what does static mean? Motionless, at rest. Dynamic means moving. Okay. All right. They kind of fit this, kind of, but not exactly. Static stability, I want you to think about that as referring to what happens immediately. Immediate response. Think about immediate response. And think about dynamic as overall or over some period of time. Overall response. And the response I'm talking about is what happens to the aircraft in pitch, roll, or yaw, depending on which one of those stability things we're looking at. So let's say that we're flying the airplane straight and level, just like that. That's our direction of our path right there. And we're trimmed. Do I know what it means to be trimmed?
Yeah, basically it means to be like have the elevators at a certain position so it keeps the aircraft stable.
What he said. Exactly what he said. You're not having to apply any force on the controls. Rudder, aileron, or elevator, if you have trimmed on all three surfaces. You have it trimmed out so that you can take your hands off and the airplane is just, it's kind of like the poor man's autopilot.
Yeah,
It's just going where you don't have to apply any force on any of the control surfaces. You're in a trimmed condition. All right. So let's say we're flying this way in a trimmed condition. Hands off. I take the stick or the yoke, I pull back. I just do it this quick. Pull back and let go. Okay. So we're going to pull back and the airplane is going to divert from its path in that direction, right? Let go. What happens immediately after I let go? That determines, or that dictates, that defines the static stability of the airplane. What happens immediately after I let go? Okay? And these static and dynamic come in three forms. They can be either positive, so you could have positive static stability or positive dynamic stability. You could have neutral, or you could have negative. So static stability could either be positive static, neutral static, or negative static. Dynamic stability could either be positive, neutral, or negative. All right? So looking at static stability, what happens next? What happens next will tell you what kind of stability, what kind of static stability it has. If the nose begins to want to go back and return to where it was, you have positive static stability. So if you let go and the nose immediately wants to go back, hey, I don't like that, let me go back where I was, you have positive static stability. Positive. If the nose wants to just stay right there, you let go and it says, oh, okay, we'll do this for a while. You have neutral static stability. And if it wants to get worse, you have negative static stability. Okay, so you have positive, neutral, or negative. So I use the example of flying longitudinally. We pull up, but it will be the same thing in roll. If I roll the airplane, if I do this, when I let go, I go this way and I let go of the stick. What happens? If it wants to start coming back, I have positive roll stability. If it wants to just stay right there, I have neutral roll stability. If it wants to get worse, I have negative roll stability. If I'm flying along and I step on a rudder and the plane yaws and I let go of the rudder, if it comes right back, I have positive yaw stability. If it stays right there, I have neutral static yaw stability. If it wants to swap ends, you never want to be flying a plane that does that. If it wants to swap ends, you have negative static stability in yaw. Okay, so you can see how this works on all three axes. All right, so that's static stability. What happens immediately after I stop the input that took me out of the trimmed condition? All right, that's static. Dynamic stability speaks to what happens over the next few seconds or minutes or whatever. What happens overall? Where does the plane go? So let's assume I have positive static stability, neutral static, positive static stability. I let go, the airplane comes back in this direction. Is it going to get here and then just find the altitude it was and then just immediately go right back to level flight? No. It's going to diverge below and it's going to build up speed and then build up energy and climb and it'll do some oscillations and it'll eventually go back to...
Not like a wave, it dissipates.
It'll dissipate, yeah. The perturbations will dissipate over time and you'll go back to a level trimmed condition. Now, it may not be at the same altitude you're at, but you're going to go back to that trimmed condition. That would be positive dynamic stability. Okay? If you had neutral dynamic stability, then what would happen is these oscillations would not change. You would just have that same sine wave all the way, till everybody starts throwing up in the airplane. That would be neutral dynamic stability. And that's in all yaw. Plane would start doing this. Roll, the plane would do this. Right? That would be neutral dynamic stability. And then you can imagine what negative dynamic stability would be. They would get worse and worse and worse until the stresses on the airplane cause parts to start falling off.
Just falls apart.
It fall apart. Okay, so from a stability standpoint, what do you think we want? We want positive, positive. We want positive static stability in our airplanes. We want positive static stability and we want positive dynamic stability. Is there any time you'd want neutral? Yeah, there is. Huh? Yeah. Can you think of an example of airplanes that, and by the way, the stability of an airplane is designed into the airplane, but we as pilots can screw it up. We can screw it up by the way we load the airplane, by where we put people and baggage and cargo can screw up the stability, because when we put cargo in the airplane, this center of gravity will move. As that center of gravity moves, you upset the apple cart of how the airplane, how stable the airplane is, especially in pitch and in yaw. Okay? We'll talk about that when we do weight and balance, but understand we can load it such that we take an airplane that was designed to be statically positive and dynamically positive and turn it into one that's neutral or negative. All right.
Would not be the best.
Which would not be the best. All right, so neutrally, you can design an airplane to be neutral, to have neutral stability characteristics, and they do, and they're called aerobatic airplanes. Aerobatic airplanes are designed to be more neutral in their characteristics, because when you're doing aerobatics, when you pull the nose up on, like, say, a 45-degree line, you don't want it to come back down. You want it to stay there because you want to pull it up and then maybe just have it start rolling up that line.
Kind of like the extra 300.
Like the extra 300. That's a much more neutrally stable airplane. Okay, and the farther away from the stable airplane you get, the more you as the pilot have to fly it, the more uncontrollable it becomes. So the more stable an airplane is, the more controllable it is. The easier it is for us to put the nose, to put the nose there or point the nose there, and it kind of wants to, or if you take it out of a trim condition, let's say, it wants to go back. So it's controllable from that standpoint. The more neutral or negative it becomes, the less controllable it becomes. It becomes much more maneuverable, but a lot less controllable. So when we talk about stability, there's two other things we refer to. We refer to stability, controllability, and maneuverability. So all three of these things you could get questions on, and you read about them in the book. So stability, we just talked about. Everybody understand stability? Okay. The more apt the airplane by design or loading is to return to its trimmed condition, the more stable the airplane is. The more stable an airplane is, the easier it is for us as pilots to control it. Okay? But the more stable and controllable it is, the less maneuverable it is. It's not very maneuverable. You're not going to go do any dogfights. You're not going to whip around and turn on a dime and do things like that, because it wants to return to where it was. It doesn't want to divert. It doesn't want to go this way. It wants to stay where it was trimmed. The closer we get those two forces, the more neutral we get, the harder it is to fly, the harder it is to trim it and keep it from, getting off its trim path, but the easier it is to turn on a dime, the more we can maneuver that thing. And when we get totally uncontrollable, we get the CG, let's say back here, relative to the lift vector. Now we get into a totally uncontrollable or totally unstable airplane. Now we get something that is completely unstable, completely uncontrollable. We can't fly it, but it's really maneuverable. It'll just whip around, so you can dogfight that thing, right? So now you're getting into the realm of fighter jets. F-18s and F-35s and those guys. Those things are so unstable that a human being cannot fly it. It takes a computer taking the input from the stick that the pilot inputs to the stick and moving and sending that to the control surfaces, so the pilot doesn't destroy the airplane, because it can't be humanly flown because it's so uncontrollable. But it is really maneuverable. Okay, so there's a spectrum of stability, controllability, and maneuverability on the airplane. All right. I want to just quickly show you what weight effects do to the aerodynamics of the airplane, okay? And I want to show you why, and I'm going to relate this to load factor. So in this example that I have here, I've got a 2,000-pound airplane, and let's be more realistic. It's probably going to be something more like, let's say it's 100 pounds. I'm not even sure it'd be that, but. All right, so the total load on the wing is 100 pounds. So this, in this example, is 2,100 pounds. We got to generate 2,100 pounds of lifting force to keep this thing flying. Everybody see how that could work? Or how that works? Okay. In the example, I cannot change my wing area. I can't make my wing grow, right? Can't do anything about the wing. Can I do anything about the density of the air that I'm flying in? Nope, can't do anything about the density of the air that I'm flying in. So I've got two things to work with. I've got the coefficient of lift, which how do we as the pilots change the coefficient of lift? Pitch the nose up and down. When we pitch the nose up and down, we're changing what? The angle of attack. You say that? The angle of attack. When you change the pitch, you change the angle of attack. So it's by changing the angle of attack, by doing this, that we're changing the angle of attack. It's also, the pitch is changing, but more importantly, the angle of attack is changing. Angle of attack and pitch are not the same thing. They're not the same thing. What is pitch? We know what angle of attack is, right? Chord line to relative wind. What is pitch?
Attitude angle of the lateral axis.
Not lateral. Longitudinal. Longitudinal and what other line? No, the angle between the longitudinal axis and the earth. That's pitch.
That's where your nose is pointing.
It's where it's so here, example would be if I hold this airplane in this position, is that a nose high pitch? Yes. Is that a high angle of attack? It's not? How do you know?
Because the airplane's going to want to continue.
Well, how do you know which way the airplane's moving? You can't answer the question. I didn't show you the relative wind. If the airplane's flying like this, it's a zero angle of attack. If the airplane's flying like this, it's a high angle of attack. If the airplane's flying like that, you're basically stalled because it's a really high angle of attack. So to see angle of attack, you have to visualize the chord and the movement. I can take a snapshot of an airplane like this and you can immediately tell me by inspection the pitch attitude because you can see it relative to the earth. So you can see the pitch attitude. You can't see the angle of attack unless you can visualize movement. This is a high angle of attack. This is a low angle of attack. This is a high angle of attack. Same pitch attitude, different angle of attack. Here the pitch attitude and the angle of attack are relatively the same. Here the pitch attitude and the angle of attack are completely different. Okay? So recognize there's a difference between angle of attack and pitch. Okay. Where was I going with that? I was going with weight and how we affect this stuff over here. So I'm not changing my airfoil shape. All I can do to change this number, is change the angle of attack, right? So if I change this and this goes up, now think about equilibrium. These two multiplied together, once we're in equilibrium, have to equal 2100. They must. This is a, what does that mean? It means equals. That means everything on this side of the equal sign equals everything on that side of the equal sign. Let's go back to math class. So this times this has to equal 2100. So if I increase this, what must happen to the speed? It must go that way. So that shows you right away, as we increase the angle of attack, what happens to the speed? It decreases. As we decrease the angle of attack, what happens to the speed? It's got to go up. Okay, so because it's got to maintain equilibrium with this guy over here. All right, so let's say that, and I want to relate this to load factor and stall speed, because I already showed you that as the load factor, as this number gets bigger, the bigger this number is, the faster the stall speed, right? The faster the stall speed. So you can already see by banking, I showed you by banking the airplane how we increase that resultant vector, and that increases the total load, and when we increase the total load, the stall speed goes up, all right? But we can also increase the stall speed by changing the center of gravity. So if I had the center of gravity out here, I'm going to over-exaggerate this. Let's say I had the center of gravity way out here, okay? Well, it's still 2,000 pounds. I'm just moving where the weight is concentrated. It's still 2,000 pounds. But now what did I do to that nose down pitching moment? It's a big one. So what do I got to do with this? It's a big one. So what happened to my total load? It went up. So if my total load went up here, let's say it went to 2,600 pounds. If my total load went up, I've got to account for it here, primarily here. So I've got to increase the angle of attack. If I want to maintain the same speed, I've got to increase the angle of attack to hold that load. Guess what I'm closer to as I increase the angle of attack? What do I get closer to? I get closer to the critical angle of attack. So I stall at a faster airspeed. The heavier I am, the higher my angle of attack has to be to hold that weight. Closer I am to stalling. Closer to the critical I am to stalling. Does that, see how that works together? Okay. Okay, the last thing we'll show you here is this is in the book. You might get a test on this, might get a test question on this. The VG diagram, it's velocity to G-force diagram. I don't know why they have you question these, but anyway, they do, or give you questions on these, but they do. You don't see these in the pilot operating handbooks, so I don't know why they really ask you questions about it. But essentially what this is, the designer will come up with a VG diagram. This is basically where your airspeed indicators numbers come from. So for this particular airplane, if you were to look at an airspeed indicator and you went right along this line right here, right along that line right there, this number right here, which would be what, about 64, that's going to be your stall speed in the clean. That's going to be VS1. That's your clean stall speed right there. And then you get here, right there, 180, whatever that is, that's your caution range. That's where you get into the yellow range on your airspeed indicator. And right here, that's the red line. That's where structural damage starts happening. So that's your airspeed indicator thing right there. So what they're doing with this VG diagram is they're relating velocity, indicated velocity, to load factor. We've been talking a lot about load factor, right? Load factor, the higher the load factor, what happens to stall speed? As load factor goes up, what happens to stall speed? It what?
Increases?
It increases, right. It has to. The higher the load factor, if this is going up, what has to happen to that? If I want to maintain, let's say I want to maintain 100. I want to fly at 100. If I want to fly at 100 and I only weigh 1,000 pounds, this could be really, really low. If I weigh 2,000 pounds and I still want to fly at 100, I got to increase that. As I increase the angle of attack, because of load factor, I get closer to critical, so I stall at a faster airspeed. So this is showing you that. So here's your accelerated stall line. So everything above this is positive G's. Everything below this is negative G's. So you can see that most airplanes are designed this way, where the airplane can take higher positive G's before structural failure than negative G's. If it's a aerobatic airplane, sometimes they're even on both directions. But what this is showing us is that, hey, if I'm doing 80, this is saying that if I'm doing 80, okay, and I put a 1.5 G load on the airplane, that's where I'm going to stall. This is the non-flying area. I'm not flying any of this stuff here. I'm not flying. So this is a stall line right here. This is where I stall. This is the combination of the speed and the load factor for this, whatever airplane this is. Here's the speed, here's the load factor. When I get above that, I stall. Okay? Now, this is critical here. Look here. If I get in this area, so if I get to these speeds with that load, I start doing structural damage. I start deforming things on the airplane. If you're flying a metal airplane, you get back and you see wrinkles in the skin, and you're like, oh, maybe I put a little too much stress on that. Okay? And if you get into this area up here, things start falling off the airplane. Things start breaking off of the airplane when you get into that area.
On the wing, and now you don't see the wing.
And the wing is gone. Yeah, exactly. Okay, so that's what the VG diagram is showing, how it's relating the speed with the loads. And so you can see you can take, on most airplanes, you can take a higher positive. They're designed to take more load in a positive direction than in a negative direction. They're just designed that way. So that's what a VG diagram is essentially showing you. Okay. All right. Any questions on the VG diagram? You might get a question or two on it. I don't, honestly, I don't understand why it's asked of private pilots, to be honest with you, but it's there, so we'll talk about it. Yeah.
On the bottom right there, for the red part.
Down here?
Value, why is it when it's closer to 120, if I pull around 3.5 Gs, it's higher, but then if I go faster and pull around almost the same exact Gs, it gets lower?
I have no idea. I have no idea.
I wish he'd have been here last week.
It was Stump the Instructor last week, and you would have stumped me. I don't know. Something about this airplane shape design or something, I don't know. It has something to do with the design of the airplane. Yeah. I mean, ideally, you don't want to be, I mean, you don't even want to be in this area anyhow. Okay. All right. All right. No questions on that? Okay. All right, last thing I want to talk about for 15 minutes here is some other maneuvering aerodynamic things, and it's left turning tendencies I want to discuss. Left turning tendencies. So you guys have, for those of you that have started training, what's the one thing that your instructor tells you more than anything else? More right rudder, more right rudder, more right rudder. We always say that, more right rudder. You need more right rudder, okay? If you ever have an opportunity to go to Oshkosh or these air shows where these guys fly the old World War II propeller-driven airplanes, you look at those guys and you're going to see that all of them have a big, thick right thigh and a little skinny left thigh. Because they're just because there's so much force on that thing, and they just got to have a big, giant leg over here.
I mean, I've flown a B-51 in a flight simulator.
Oh wow! You're about. I give up.
As soon as I got about not even halfway through, it was already.
Yeah, it just goes fast. Yeah. All right. So left turning tendencies. What those are those are tendencies that cause the airplane to want to go left, and it does it because of. Can you go get me a little wooden propeller? There's a wooden propeller in there somewhere. It does it because of the gyroscopic forces that are occurring and the rotational forces that are occurring as a result of the propeller. We have 4 forces that cause the airplane to have a tendency to turn left. 3 of them really affect, during the takeoff anyway, 3 of them affect tricycle gear aircraft. One of them really only has a left turning effect on a tailwheel airplane, but I'll talk about which one it is. But because of our propeller, and we call it left turning tendencies because here, in the western part of the world, the propeller turns from the pilot's perspective clockwise. If you have a Russian engine, it's going to turn the other way. So you'd have right turning tendencies. So if the propeller's turning that way, you're going to have right turning tendencies. If the propeller's turning this way, you're going to have left turning tendencies, okay? So generally speaking, in the Western world, if the crankshaft from the pilot's perspective is turning to clockwise, you're going to have left turning tendencies. So there's 4 of them. One is torque. Torque, okay? So torque is just simply, it's Newton's third law, action, reaction. So if this is turning that way, then I have an opposite reaction in the other direction. That's torque. So if you've ever taken a battery-powered drill and you pull that, and it does that in your hand, that's torque. So as the bit or the motor wants to spin this way, the whole drill goes the opposite direction in your hand. And if you have it in reverse, it'll go the other direction. So that's torque, all right? So in the airplane, and this is primarily affects us on takeoff. These left turning tendencies affect us on takeoff because these forces are most noticeable and at play at high power, slow speeds. Where are we at high power, slow speeds? Takeoff. So that's why we experience them all the time, but that's when we really see them. Okay? The forces are always there. So on the takeoff roll, as soon as we get that power in there, okay, and we start rolling this way, we start moving this way, we have a rolling force in this direction. Now you think, well, how's that going to cause us to turn left? Well, what it's doing is it's putting more weight on this left wheel. And you have more weight on that left wheel, which gives you a higher drag amount over there, and that by itself causes the nose to want to go left. So you have a rolling tendency, and torque is the only one that's a roll, okay? Torque is a roll. The other three are a yaw. Torque is a roll. That roll exhibits itself on that left landing gear, which then causes a yawing effect. But the torque itself is a rolling effect. Okay? That's the first one. That's the easy one. That's torque. Then we have spiraling slipstream. Spiraling slipstream. So if you picture this plane, this propeller turning in this direction, okay, as that air is coming off that propeller, it's spiraling around the airplane here. It's spiraling around the airplane, and as it spirals around the airplane, it hits that rudder, and it yaws it to the left. It hits the rudder and the fuselage and the whole thing, and it yaws the airplane to the left. So that's spiraling slipstream, okay? And the reason that that's at its maximum is because the slower we're going, the less effectiveness that rudder is going to have from a stabilizing force, the horizontal stabilizer, the vertical stabilizer is going to have from a stabilizing force, and the less effect the rudder has to counteract it because we're not moving very fast yet. The faster we're going, the more the rudder just kind of straightens us out like feathers on a dart, okay? So that's spiraling slipstream. The airflow coming off of that propeller, spiraling around, it's hitting the tail, turning the nose to the left, okay? Spiraling slipstream. The other one is asymmetric thrust. Asymmetric thrust. We call it P factor. The book calls it P factor, but I like the term asymmetric thrust because it's more descriptive of what it is. So picture the propeller here. Look at the propeller from the side view right there. Look at the twist in the propeller, and think about how, based on the discussions we've had, how this, as the propeller is moving down like that, think about the angle of attack and the lift that's being generated, right? The force that's being generated in this direction. Can you picture that? So as we're flying like this, the angle of attack here, this propeller blade is moving down, this one's moving up, but the angle of attack here is identical to the angle of attack here. Can you see that? Okay, so this half of the disc is generating the same amount of thrust as this half of the disc. But as soon as I pitch the nose up, I've changed the angle of attack of the downward blade versus the upward blade. And now I have much more angle of attack over here than I have over here, which means I have an asymmetric amount of thrust on that disc. This side of the disc is generating a way bigger thrust vector, and it's causing me to yaw to the left. So when you get going on the ground, and this is where you usually see it. You get rolling, and you need a little bit of rudder there. You need a little bit of right rudder because you've got that spiraling slipstream, and you've got the torque, and you're going a little bit to the left, and you got it. And then you pitch the nose up, and then it really goes. And that's why, because you pitch that nose up, now you have that asymmetric thrust, and there it goes. That's asymmetric thrust. Okay. The last one is gyroscopic precession. This one helps us actually in tricycle gear airplanes. It helps us. We talk about it because it's detrimental. It's not detrimental, but it is a left turning force on a tailwheel airplane, but it's not really a left turning force on a tricycle gear airplane. It's actually a right turning force. But here is gyroscopic precession. So when you have a gyro, a spinning disc, okay, it sets up forces. And so your propeller is a spinning disc. And from a pilot standpoint, the disc is spinning in that direction, right? All right. When you move a gyro, I don't know if you can see this, I'm just going to pitch it. The whole gyro moves in a different direction as I move it up and down. It goes in different directions. That's gyroscopic precession. And I'll let you play with it. But essentially what gyroscopic precession says is, if I'm not moving this disc, it wants to stay in that plane. It wants to stay right there. It doesn't want to change. But if I apply a force, and if I applied the force here, the disc, let's say it's spinning. If I apply a force here, the disc is not going to want to do that. That's not what happens. The force precesses because of the gyroscopic stuff that's going on. So I'm applying the force here, but it precesses 90 degrees, and it's felt over here. That's gyroscopic precession. Wherever you apply the force is felt 90 degrees in the same plane of rotation. So if I apply the force here, it's felt over here, okay? So if I'm in a tricycle gear airplane, I'm rolling like this, as soon as I pitch the nose up, I'm applying the force here, it gives me a right turning tendency. So it actually kind of counteracts the left. But the gyroscopic precession is only in effect while the disc is moving. As soon as I stop it from moving, that force goes away. You still have the other forces in play. That force goes away. But if I'm in a tailwheel airplane, I'm rolling down the runway, I've got my torque, I've got my, in this case now I've got asymmetric thrust right there because the propeller's on a plane like this, and I've got spiraling slipstream. Then as soon as I lift the tail, I've got an additional force, okay? So I'll let you guys play with this. Just hold it like this, spin it in a clockwise direction, and then just move your hand up and down, and you'll feel it moving. You'll feel it moving in, pass it down. Feel it moving, you'll feel the precession that's happening in it. So that's gyroscopic precession. And that's why you have those left turning tendencies. You'll notice those, just move your hand up and down. You feel it? Yeah, just pull it up there a little closer and you'll feel it a little bit better. You feel the force isn't applied where you're moving it. All right, you'll also have gyroscopic precession forces that you feel, or turning forces as a result of the spinning propeller in other phases of flight. For instance, on a power-on descent, you're going to have a right turning tendency, okay, because you have asymmetric thrust on the other side. Okay, so you'll have right turning tendencies. They're not as noticeable. They're not as noticeable because you're going much faster, and that vertical stabilizer back there has more effect the faster we're going, right? If I take a dart with a feather on it and I throw the dart, like that feather's not going to have much effect. But if I really hurl it and I have more airflow, it has more effect, right? So the faster we go, the less we feel some of that stuff. Okay, does that kind of make sense to you guys? All right, couple of questions from an evaluation standpoint. Close your notes. One of the forces, what does it mean to have forces in equilibrium? What does that mean?
Opposing forces are equal to each other.
Opposing forces are equal to each other, okay. Can we be in equilibrium while we're in a climb?
Yes.
Yes, we can. We can, yes. What we need I didn't say this, I should have said this, so maybe you want to open your notes back and write this down, I forgot to say it. The airplane is in equilibrium whenever we are in steady state, unaccelerated flight. Steady state, unaccelerated flight. So that means basically if I'm going straight and level, okay, as long as I'm not accelerating or decelerating, then the forces have equalized. If I'm in a climb, if my climb rate has stabilized, if I'm climbing at 500 feet per minute, all the forces are back in equilibrium. All of the forces acting in this direction equal all of the forces acting in that direction, and so forth. If I'm in a descent and my descent rate has stabilized, I'm back in equilibrium. All right? So steady state, unaccelerated flight, we're in equilibrium. So it could be in any condition. You could be doing this. If you're doing that and you're so stabilized, you're not having to do anything, you're in steady state, unaccelerated flight. You're stabilized. Forces are stabilized. When you're in a spin, when you're in a fully developed spin, the forces are equalized. You're in steady state, unaccelerated flight. Okay? So once the forces go back into equilibrium, you've reached steady state flight. Okay. What airspeed does our airplane stall at? Any airspeed. Any airspeed. What has to happen for a wing to stall? Increased load factor.
Critical.
Increase AOA to the critical angle of attack. You got to reach critical angle of attack. Okay? All right, and whatever that critical angle of attack is for that airfoil, that's it. That's what it is all the time, forever and ever, amen. Never changes. Okay? Now when you put flaps in, or different degrees of flaps, you're changing the airfoil, therefore you're changing the critical angle of attack for that little section of the wing, okay? But again, if you have full flaps and whatever that is, that it is, right? Okay. All right, good. All right, who here is leaving the class with more knowledge about aerodynamics than when you got here? All right, success. Okay, next week what is next week? Next week is systems. Okay, so flight controls and aircraft systems. So in 8083-25, read, I think it's just one, no, it's 2 chapters, isn't it? It's 2 chapters. It's not nearly as big as these 2 chapters that you had to read. Although systems is pretty big. Read those 2 chapters. If you have the Gold Seal Ground School, read also the accompanying or study the accompanying parts of the Gold Seal that go along with next week's class. All right. While you're reading the chapters, while you're going through Gold Seal, I want you to write down, if you have questions, write them down. And at the beginning of class, I'm going to write those questions up over here on the board so that as we get to that section, I can specifically make sure I answer your questions, okay? So write questions down as you're doing your pre-study so that I can answer them for you. All right. See y'all next week.